This is ICDL tutorial. The ICDL already was over this week. This is the Monday, and I'm sorry that I made an error. I thought that the tutorial is today, but turns out to be last week. Somebody contacted me, and I was not there. So the program chair and the general chair know that the tutorial will be given today. The website that linked from the conference had a today's date. So hopefully that those people who missed the last time could either attend today. And also I plan to record, so you should be able to get the posted version on the YouTube. I plan to post it on the YouTube. And this is a 4-hour tutorial, and it's kind of long, probably not very convenient for your time. And I plan to make it 1 hourly break. So every section will be 50 minutes. So you can have a 10 minutes break. Then we'll resume at the hour. Totally, there will be 4 hours. Although it's long probably to some of you, but still not sufficient to cover such a complex topic. And there are many, many components. I understand that you probably will use this one as an opportunity to get a snapshot of what is available, so you can continue the future learning. And we welcome communication and questions. And if you have a quick question, you can ask right away, because we do have some time for questions at the end. If you have extensive questions, probably you want to leave at the end of the tutorial. That will be about, in the Eastern time, it will be 1 p.m. And in Beijing time, it's about 1 a.m. So it's kind of late. Appreciate it if you can get to the end. The title of the tutorial is Conscious Learning by Developmental Networks. We cover some major topics like vision, audition, natural languages, planning, and thinking. Now, you probably thought that there are other topics that conscious learning can handle. And this is just a few simple issues. Now, you probably know that, for example, the vision is very complex, and how you can program it. You probably want to program each problem. Many people are doing that, except our group. I think that vision, audition, natural languages, including planning and thinking, is hopeless without doing conscious learning. So conscious learning is not just a luxury or fancy topic to address, but I think that's necessary, and you'll get to that in the tutorial. And I hope that you will realize that the landscape of AI will change very soon. Some of the issues that I will talk about the current problem of post-selection and the misconduct that has been prevalent could be addressed very soon by the community. Now let's get into the topic. I talk about the first about the history. Then I discussed Turing machines. Many people said that we don't need the Turing machines. It's not true. Even for just vision or pattern recognition, you also need a Turing machine. Then I talked about variations. The variation very useful for us to see how our general purpose computers has many hardware and software that boils down to the same type of machine, because the Turing machine is sufficiently general. Then we discuss universal Turing machines. Some of you probably have heard Turing Award, but you probably also heard universal Turing machines, but you're probably not familiar with how universal Turing machine was modeled by Turing machine. There is the coding issues, and I will mention a little bit because that's too much detailed, talk about the coding, but the coding idea is very important to understand how human code general purposes. And that's a natural language, actually. But not just natural language alone, okay? Not just, but natural language is very useful. Plus like sign language, give me that poem. So if you nod, yes, all right, it's a coding, it's coding. And then this number 5 is extremely important. Basically, it said that the control of any Turing machine is a finite automaton. That's extremely important theoretical result, so that if you have appropriate neural networks that can approximate a Turing machine using finite automaton, so the necessary condition for any neural networks to be able to do neural network like automaton, like FA, in EE, it's called a finite state machine. Then you should be able to model Turing machine. Before Turing machine modeling is very complex. Now we simplified it to FA. Then I start to discuss developmental neural networks. And that includes many, many topics, and probably would not be sufficient to get everything in this tutorial in 4 hours. And I encourage you to take a course of Raymond Institute, 871, and many people have taken it, and then get all the details of developmental networks. Number 7 is about the theory. We have many papers talk about the pattern recognition mostly. They did not understand that you need a theory that break away from pattern recognition. And why we have a misconduct in deep learning, because deep learning guys, they don't have enough theory to understand the problems. So I talk about theories. Then I would discuss how a neural network like DN, developmental networks, can emerge a universal Turing machines. We have not done everything yet, and that's the theory, and with some experimental example about the possibilities and the experimental result that give you a snapshot of possibilities. Then I addressed a series of experimental work that conducted by many researchers working with me, that vision, audition, natural languages, autonomous programming for general purposes, including planning and thinking. Then I talk about conscious learning. Now you probably say that we have 10 topics. We'll not be able to discuss conscious learning until we have all the legworks that covered in the early chapters. Then the conscious learning is a fully autonomous learning. And I'm saying that unless we have some simulation right now in the virtual world, the real world, 3D to 2D to 3D fully conscious learning is what animals do. all the animals, including fruit flies, horse, cats, monkeys, they are all doing this autonomous learning. But interestingly, there's no machines yet or robots can do that. And that will be a game change in the AI. That's the only way to do conscious learning. And you need a lot of techniques and brain modeling that's ready in order to do that. So first one, to talk about the autonomous mental development that started from as a milestone of the history. The reason I talk about the AI research, including natural intelligence research, is that human has endeavored into natural intelligence from very early on, given Socrates, Plato, and Aristotle. That's 500 BC. And although there are some very interesting work going on in Europe, and I have a book coming up, why Europe developed faster in the modern days than Asia. There are deep reasons. That's a part of consciousness. Because the geography, you probably laugh at me. How come geography play a role in modern day development? And the book will come out maybe beginning of next year, because I already agreed with publisher that we are finished in my draft by the end of this year. Basically, it was human just like animal, and we think like animals, and we got restricted by the geography. And look at the maps of the Europe. You see the Europe is the peninsula of peninsulas, and it has a very rich structure of the waters. And although we have coastal lines in other words, but not as complex and appropriate size, the water size and the land size, that cause tremendous competition, many wars in Europe. So Europe is not because of white genes are advanced so that they advance earlier. That's not true. Not because of genes, but geography. That's what I discovered after I had a brain of mind, a model. Then I discovered that we are very much shaped by geography, very much like Charles Darwin did. Charles Darwin basically is the animal evolved through geography, the land, in his case is the island. And the same thing that's true with human. Then we have later, 1500, we have Leibniz, Locke, and Descartes. Then we have Pavlov, you probably know Pavlov learning models with Zondike. Then the 1900, we have a high in neural networks by Lumhard and J. McCullen. AI is about machines, so that would not have started till we have a first machine. That's the time that, unfortunately, that was during the Second World War. Alan Turing had a chance to look at the first computers, and that we start to have AI. So AI started very late, 1950s. Then because this subject is so complicated, then there is a fragmentation in natural intelligence and artificial intelligence. And natural intelligence at that time, without computer as a model, then without computation, Then with artificial intelligence, at the early on, the same true with myself actually. There's little understanding of neuroscience. At that time, many people said that human brain and many areas are dormant. They are not really active because at that time, very little understanding of the brain. The technology and instrumentation helped a lot in the understanding of the brains. And then the fragmentation, basically the very narrow-minded view of natural intelligence and artificial intelligence still prevail at present. And I'd like to discuss Alan Turing. And although we have a von Neumann machine as a model, but a von Neumann model is different from Alan Turing's machines. He had the theory. Theory is extremely important. Just say I have an instruction, we have a program. It's not as clear as a theory. Then 1950, and I think that we respect Alan Turing very much because he probably was the only guy that has of course, an AI gets back very early. We have even people talk about the games, using computers. But the first well-recognized paper by Turing is 1950, and he raised the well-known problems: can machines think? And I think that we have answered this problem, although not really in actual machines. We don't have a robot really can demonstrate thinking like a human, at least like a horse, for example. But the theory has been more or less solved. Then AI already have 17 years. The problem of AI is that we have many papers. Right now, AI was so hot that it turns out to be, we have so many papers in every conference. Very interesting, but most of the work, I think it's on the wrong track. Identified as a post-selection. I will get to that at the end. Then autonomous programming for general purposes, APFGP, is necessary for any AI problems, including vision, audition, and the natural language processing. Then the first paper about conscious learning, it's not the first time that some people talk about the consciousness, all right, because I would review a little bit of consciousness. They are qualitative. They are not algorithm. The first algorithm for conscious learning appeared 2020. So now we are in a good picture. Symbolic AI has been starting early days, 1950. Many people said that connectionist later. It's not true, because Alan Turing's paper talk about the logic that's clean and analogy and scruffy by Marvin Minsky. Then Marvin Minsky said that neural networks are scruffy, basically dirty, without theory. And of course, a neural network is harder, much harder in terms of series and logic. I get to that later. But the time that both approach was proposed was at least 1950 by Alan Turing. And in his paper, he proposed that you have a brain-like machine that has neurons that connects and then learn like a human. And then I think that symbolic AI is clear and easier to do some work and publish. That's why we have early on we see a lot of symbolic AI work. But then later on, we have a high right now for good reason or bad reason, very high in neural networks. And AI is talked about in almost every high-tech talk, including the leaders of big countries. Then we are facing a unification. And what's the unification? And I propose it's the APFGP, auto programming for general purposes. Now, a little review the flavor of symbolic school. AI has two schools, symbolic school and connectionist school. And now we have a developmental school, but I will talk about two schools before I talk about developmental school. The symbolic school, basically, once you have a pattern, right? It's a pattern recognition in the 1986 by Kingston Fu. I think he is very well known in pattern recognition. He modeled the strokes for letters by symbols. And basically, you need to detect the strokes. In this case, it's E. Then you need to detect components. Then you look at the relationship between the components, you recognize E. Nowadays, we are using neural networks. So it's more flexible, but still in very much, it's a symbolic school because we have labels. We have labels for the strokes, for example. So if you do careful work with neural network, you start to labels, symbolic labels for the strokes or parts. They are symbolic schools. So by symbols, what we mean that we define a set of class labels that are defined by symbols. The meaning of the symbols are in your mind or in your design document or in your papers, and the machine never reads those symbols. So that's a machine are really, really dumb. They don't understand symbols. Although they classify the pixels into symbols, but there's no way for them to understand the symbols. And so this is a very, very fundamental problems. So in the case that, give example, I was using autonomous driving for lane centering, and the machine will break if the condition like a curve is too sharp, then it will break. Then the alarm sounds up because they had no idea of why we need to track the lanes. They had no idea. They did not know that it is tracking well or not well. So the machine does not have a way even to evaluate the task. So if the machine cannot evaluate the task, the machine will break. And all the animals, including cats and horses, they can evaluate. They're doing tasks. Their task is probably simple. They will not understand human language, but they understand they can get home or not, right? If they couldn't get home, they thought they get lost. They start to wandering around a little bit. Then they get a familiar thing they can get back. They will not break. So it's extremely important. I think that's extremely important that we must conduct autonomous learning where the learner is able to evaluate how well it is doing a task. And further, what tasks they need in order to do reasonable job to recover from a possible failure. That's conscious learning. Now, connectionist, and I'd like to mention Fukushima, Kinehiko Fukushima. It is not like I'm biased in favor for Asians, and I think the Asians did great work in the modern days. I'm not talking about the racism, I'm not, but I mentioned neural networks, but in the connectionist, Fukushima give me the most guides in terms of how to do vision, all right? Although his task is simpler, because you have so many things to do, you cannot do everything altogether. So he started with a single letter, in this case, numbers 0 to 9. Then he was doing basically labeling the single letter from 1 to 9, for example. But his bright idea is from local to global. Basically, that he has neuron that has a small receptive field. Then at that time, although he manually pick up the neurons, it's like a human is in the loop of feature selection, which is limited, but we need to understand now. All right? At that time, he probably did not think that's a major problem, but many things that we take for granted turns out to be a major issue. So he has from local to global. That's the bright idea. But selection of the feature by hand is a very fundamental limitation. Then he has a simple cell, complex cell, simple cell, complex cell, and his hierarchies. And the complex cell did not really doing learning, and the simple cell is doing learning. And basically, so that's the architecture he had. It's a feed forward, did not have a top down. Then let's look at what we proposed in 2000. We proposed to a National Science Foundation and DARPA, Defense Advanced Research Project Agency, is that we must do development. And I use the term learning so that we can attract some people, because if we talk about the machine learning using development, people don't understand. What do you mean by development? Development in Chinese is 发育. It's from the this prenatal birth and postnatal birth. So you need to talk about how humans understand the tasks. So you must go beyond tasks. And this workshop at the first ICDL conference turns out to be now gets more participants. I really appreciate those people that had ICDL 2022 in London. But unfortunately, those volunteers, although they did great work, they followed behind too much. They did not understand that development must be task non-specific. So the paper it's a policy forum published in Science. It's a task non-specificity. That's the flag. Many people, earlier leader of the field, including, I don't want to mention names, they're a good friend of mine. They wrote a book and published by MIT Press, but turns out to be missed the boat. They said they will improve, but hopefully they will improve. They missed the boat of the task non-specificity. In other words, when we have a baby, do you think that they know the tasks? They have no idea of the tasks. They just respond that gradually they have an idea of what to mean by task. Then gradually they understand the context as a task. So the genome-like program is like a developmental network. We'll talk about a lot in this tutorial, but only 2 pages long. And there is ICDL conferences. We have ICDL conferences. Then we have AMD technical committee. It's unfortunate. Later leaders, volunteers, they dropped AMD. They make IEEE transaction to become cognitive learning and development learning, cognitive developmental learning transaction. And the first transaction in this series is IEEE transaction on AMD. And that's okay, but it's kind of bad for development, because you mix with AMD, transaction AMD 2009, we solved so many problems. In IEEE, you need 9 committee to approve. And so the Microsoft researcher Zhang Zhenyou, I really appreciate he worked very hard with the community, then get transaction approved 2009. Unfortunately, it becomes named and changed to cognitive and developmental systems. Then we have wherewith networks 1 to 9. Then we have APFGP. And now I talk about a larger scope of deep learning. However, got the error background. Many people, you probably did it, don't feel bad about it. I think that the practice is a fraud. I get to that. Then Fukushima did a 2D pattern recognition. And 1991, I worked with Naranja Ahuja and Thomas Huang at the UIUC. We had a perception in Chinese. It's called Shenzhang Wang. And it's the first deep learning for 3D and has new ideas, 7. Then ImageNet came up. And I'd like to ask, I'd like to thank actually Fei Li for organizing this network. She's a good friend of mine. I appreciate it very much, her great work. But unfortunately, maybe because I think she's a great scholar, but probably she did not have enough training in computer science. I don't know, because she did not understand that you have a constraint. When you do a competition, you must have a constraint in terms of the limit, in terms of hardware, for example, right? In terms of how much time it takes. Maybe it's difficult, but at least you should restrict the number of neurons. You cannot ask the Google to compete with a university professor. And Google had like 30 or 20 people work on the network, many computers work together and not get to the flow part of it. I think it's a flawed. And they gave you superficial performance. That was really bad. That's how it became popular. And many government money gets wasted. All right. So the history happened that the Google, I like to get Google funded DeepMind 400 millions. But turns out that's a starting point of a huge scale plagiarism and fraud in AI. Now, our work over here with my colleagues and co-workers, like many, if you go to the website, including nowadays like Zhejia Zheng and Xiang Wu and others. And I start with the symbolic school. I'm sorry, I made an error here. It's 1984, not 20. 1984, when started with the master at the UIUC, and I was doing symbolic AI, was doing motion and structure from image sequences, and I graduated 89 with a PhD. And then after I spent 1.5 years, and then I got back to UIUC. Thank Thomas Huang and Naranja Ahuja for sponsoring me. And I immediately start to do perceptron. It's a connectionist for 3D. And Thomas Huang said that John Weng is ambitious. I tell you that I admit it, I'm overwhelmed. I did not know how to solve so many problems in the 3D vision where you have cluttered word. Over here, we assume a single rigid object, right? We only recover structure and motion parameters. Now, suddenly here you have a cluttered word. You have so many objects, and you want to analyze what's going on. So overwhelmed. So that's how new cognition by Fukushima helped me. And then we have Perception in 1992, and this is a well-known conference. IJCNN is a well-known conference in connectionist. International Conference Computer Vision 1993, it's the best conference on computer vision, arguably. And International Journal on Computer Vision is the best journal on computer vision, arguably. And many people, there are the better journals. But later on, plagiarism happens. They copied the idea of perception without citing. Sorry, you coming in, guys, please mute your microphone, please. Then I had a sidetrack because at that time software was slow. So I was doing short-lived, and because the classification is too slow from images, and it was self-generating classification tree. And I look back, it's probably a strategic mistake. Because once you look at classification tree, you treat entire image as a single monolithic entity. That's bad. Many people start to do a neural network. You want to understand. You want to do local to global and global to local, back and forth. At that time, we are doing local to global here, feed forward. But we did not understand that you cannot just do with speed using tree without doing local. But if you have local, you have too many trees. Do you see the problem? We have too many trees. So that was something that we cannot deal with. So we must share features among many, many classifiers. That again, it's a developmental network. So we get back to neural networks, and we start to use concepts, more general concepts than just labels. We have labels where what? So those are the property of entities, not the class label, not the class label of objects. So we have what networks 1 to 9. Then from 2018, we had a problem. We realize problem, basically when you do the work, you realize problem when you're doing it, before you even did not know the problem. The problem is that you have a brain areas. Once you have a brain areas, you have a connection between areas, you got stuck. So all the connectome projects, including NIH projects, they are useless in terms of modeling, all right? Not useless in terms of get more data, but we don't need those detailed data. We don't need them. Sorry for those guys that spend a lot of money on connectors, including people in China. And a good friend of mine was heading a connectome project in China, and he supported me so much, and I feel bad to talk about the problem of connectome. I'm sorry that connectome is useless because we already have a global connection pattern of the brain, Van Ansen, and that's enough. For theory, that's enough. You get more data, more connections, they're useless. That's what you need, fluid hierarchy, because brain will get the detailed connections from experience, and the connectome will not get to that. All right, each neuron has its own competitors. If you have areas, then each area becomes a global competition within the area. That's bad. So each neuron inside each area needs its own competitors. That's extremely new idea, and I'll talk about that. Then later on, from this year, first paper appeared January this year, after rejected by respected establishments, and history is repeating itself. They reject our papers, And that's the first papers about conscious learning was rejected by Science, by Nature, by PNAS, by my communities, neural networks, conferences, and even neural network journal reject my paper, first paper on conscious learning, and they did not even want to review it. There was really something happened, just like a Copernicus time. I just felt that I was probably not as important as Copernicus, but the time was just like the old days. Then we have cost to find ME, I'm sorry, brain patterning. So we start wire entire brain totally autonomously when the skull is closed. Then everything needs to be real time. Learning must be on the fly, on the chip. So we have an issue of a brain chip. So we are starting to do brain chip designing, and that's something that not familiar to me. And I was old, and I already retired last year from MSU, so that I can work on brain chip, and that's how I start to work with much younger students to design chips. And we have a lot of engineering issues. So without brain chips, AI is hopeless. Now, these 7 ideas, I just get to a little bit. All right, it's a 3D. It does detection and calculation at the same time. It deals with different scales or sizes and using resolution. And I tell you that resolution is bad, actually. It's not resolution, actually. At that time, we called strides. Later on, they called stride. I did not use it. I just use resolution. And then you have you need to match large objects, right? Large objects have details. Then you want to match local to global. That's a huge problem. Then we have a subsampling in the network. And I have a position blurring. Some people use this idea too, but did not cite. And max pooling is very well known. George and Schmidt-Huber wrote a paper that he said that we are the first paper that doing max pooling, although we did not use the term max pooling, but they only use this idea, but they did not cite it. They should at least cite it, right? And because the first neural network was 3D, deep learning is hard because doing 3D, and we should cite it. And otherwise, it's a plagiarism. And we also do segmentation. Some recent paper are doing segmentation, and send an email to the well-respected friend of mine in Chinese academic science. He's a member of academic science now, and congratulations to him. I said that we did that. It's 1991. We did that. All right, we segmented. We classified. We also segmented from the collected scene. So celebrities, I describe them, the big shots, selectively plagiarized it, all right? And I cited Fukushima, and we have Cresceptron, Ian Lacombe, and Joshua Benjo plagiarized it. Tommaso Poggio plagiarized it, I think. I cannot say that for sure because it's up to the court to decide. Li Feifei, Ian Lacombe, and Yunin, good friend of mine, sorry. Jeffrey Hinton, many Google papers plagiarized Cresceptron. All right, they used the idea, many ideas or new ideas from Cresceptron, they did not cite it. So I had a paper with a YouTube talk. The Turing Awards go to plagiarism. It's a question, all right? Don't say that I slandered you, all right? I defamed you, and I know the rules of defamation. You have 4 rules. The first rule is what I said is false, and I can prove at the court what I said and provide evidence to justify what I said. And neural networks are in crisis. They're open skull, and the people were supervising neurons.
because they understand the task. They know that what neuron they need, including well-known ones like HMAX, like OSTM, like SOM, or adversary networks. Then do post-selections, because they train many networks, each start with a random guess. Then they drop data, and drop data is misconduct. Then how to avoid this? And we perception only train one network. Perception train only one network. So even at 1991, we avoid the data deletion issue. Then we have optimization. One single network is optimal from DM. So what do you mean by connection next score? Connection is the score now. It's getting very hard. Congratulations to Georgia Hinton, Joshua Benjo, and Ian Lacombe, and they got the Turing Award 2018, and I think that their work is a copy, and the behavior is a plagiarism and falsification, and I'll get to that. Connection is school, and stuff from 1950 that neuron-like. Many artificial neural networks are symbolic, although they say connectionist, because they use the label, class label, and the same feature in the network, like STM, they use symbol features that are symbolic skill. It's not totally symbolic, it's a partially symbolic. The black box doing data fitting and doing post selections. Less brittle? Not really. So I alleged, I remember the term I said, I alleged flawed in Turing Award. Then the limitation, there are many limitations. The most limitation I can say is first is open skull. Human is in the loop of development. Is your mother in the brain when you learn? No, your mother is not. So you cannot have your programmer into the network. It cannot. So the computation and learning of network must be totally autonomous with skull closed, right? Then we have a limitation of the post selections, and you train many networks, you drop many networks without reporting them, all right? And no statistical validation, right? No cross validations. And why neural networks have huge local minima problem? And some people said, no, there's no neural network problem. That's a lie, right? You look very close. They only do local analysis. So suppose I have objects, right? You have background, you have background, you have objects. Then even your receptive field is reasonably small, but how they can go to the class label? And human, if we're doing inside the supervision, that's a flawed, right? And neuron did not know how give an example, this one detects this pattern, this one detects this pattern. How do these two neurons know that we are doing the same task, or we should not doing the same task? There's no competition. So without the competition, you will not be able to figure out who's doing what. So without competition, that's an error backprop. It's like Chairman Mao, sorry, so people probably will ask questions. Sorry, I'm not saying that everything about Chairman Mao is bad, all right? So Chairman Mao wants to do a planned economy, and he wants to increase your productivity to catch UK, but he did not know the detail, right? So he wants to get the superficial numbers. Superficial numbers without knowing that these companies or individuals want to do competition. So planned economy like China did between 1949 and in 30 years, it's without competition. So we need the competition. So you have competition, and then I win here, and then I make noise, and I will connect it to the later neurons. So competition is the key. If you are doing error back plot, all right, drop them right away, right now, all right, because it's useless. It's like Chairman Mao. Now, people said, look at the data. We do have data. This is the luckiest network, right? So Jatin Trent, he told me that 7. I don't think 7, more. He said he tried 7 network, then he dropped 6, and he picked the luckiest one. And how he dropped 6, he tested on the test data. So those are the test data, all right? So we already have test data that we only train, our network train only 1 network, all right? And CNN with at a back part goes down so slow. That's the first 10. That's the second 10, and this is 10th 10. That's the 20th 10, 30th 10, 40th 10, 50th 10, and goes down so slow. Even this, because this is the luckiest one, all right? Luckiest one, not even match with only 1. We start with the only 1 over here, and it's already optimal. Do you see that? It's a huge difference in the performance, but they don't read our paper. They don't even cite it. And Google, with Fei Li, published in CVPR in the same conference, they do plagiarism. I allege they do plagiarism without citing us. But we already compare. Of course, we cannot get into CVPR. CVIPR is corrupted, right? There's a paper called Paper Gestalt. And the reviewers look at the shape of the paper. They don't get into the review material, right? And we submitted to a workshop and appeared there. And I went there, and there is a paper hanging around, and because that paper was rejected. Of course, the paper will be rejected. It was talking about reviewers are reviewing papers based on superficial features, not the real material, all right? So misconducts. First misconducts in deep learning is data deletion. The second is the test on training data, because the selection of network, the luckiest one is using test data. So the test data is using like training data. Why our method was can avoid that one? Because we have retention rate, we have a learning rate, and this is the age. So you start with the rendering weights, and as soon as this neural network, this neuron wins with X input, right? This is response. Its retention rate is 0. The learning rate is 1, but age is 1. Then the input directly goes to weights. So regardless how you initialize the network, you end up with the same network, because the result only affect which neuron wins, because the random initial guess of the weights, but will not change the network. Logically, those networks are all equivalent to a single network. And we resolve this issue very clearly. And this particular paper, IJCNN 2021 paper, talk about the local minima issue of CNN. Then our paper about the conscious learning was rejected by Nature. Then I submit, you publish flawed papers, all right? And at that time, 15, all right? And in Nature, and I submitted my report, plagiarism report to Nature, and the Nature sent to reviewers. Out of 15, only 4 papers also responded. And all those responded did not really get to the issues that I was talking about. They said, oh, one paper by Google said that we we reported we already have trained 10,000 papers. Come on, 10,000 papers, you must report the performance 10,000 papers. It's not enough. They pick up like over 100 luckiest network, all right? Then dropped 90% of the network. That's data deletion, all right? And it's, oh, I'm doing reinforced learning. I'm not doing supervised learning. Same thing. What kind of mode you learn, it doesn't matter. You are doing misconduct. All right, then I talk about a Turing machine a little bit, all right? And we have, why we do Turing machine? Many people in AI know Turing machine, but people doing neural network, people mostly have not learned the Turing machine, all right? Because Turing machine is the computer science. And we talk about finite state machine. Most neural net guys know finite state machine, but they don't know how to map finite state machine, or FA in our case, to a neural network. But look at that first, all right? Suppose I have a string like that, and the double circle means accept, all right? Then you typically start with a rejection or acceptance only. You have two binary output. But we like the output of the network state. Why? Because you want to have a more output, more detailed output, so that outside know what you are thinking about. So you will output a state, not just acceptance or not acceptance, not just single circle or double circle. So output state, they call agent FA. Agent FA means the state is output, all right? Then we start into the attention. Attention means that I have a street scene, for example. We have so many cars, you have a traffic sign, we have many pedestrians. You must do local analysis for each one, all right? For any time, you must do attention, that's called attentive. Then Turing machine is able to deal with local analysis. That's based on the components. You have a tape, you have a read-write head, you have a state. Then the great part of Turing machines have a 5 tuple. I call sentences. It's just a kind of idea so they can, as a nutshell, it's a sentences. Why 5 tuple? It's the input symbol that's local. It's not the entire tape. It's not the entire image, but rather a piece of input. In this case, is symbol. C or A or T. Then they have a state. State is handcrafted, which is bad. Our brain cannot design the state by your teacher. All right, state is designed by the learner. All right, then you need to go back and forth. That's called read-write head. All right, not just read, but also write. Write, we need to act. So everybody, if you are doing pattern recognition without the action, that's wrong. You must do action, right? Action in Turing machine is the act. So if you are doing a neural network without taking into account action, that's wrong, all right? So 5 tuple, put this suggestion together, all right? Read symbol and write symbol, and the action in terms of head motion too, all right? And write symbol is also, and the old context and the new context, put that together 5, all right? And I try to put everything into nutshell so they can get the idea in a nutshell, all right? Then Turing machine are not grounded. Why? Because the tape is simple. Every symbol is handcrafted, and people don't understand it. So they say stop sign is the symbol. No, stop sign is an object, all right? By symbol, I means ASCII-like, all right? It's, you have uniqueness. In the computer, you have ASCII, for example, it's a uniqueness. You don't have to use ASCII code, you have others. But once you have uniqueness, it's called what I call symbol, all right? Traffic sign is an object, all right? So you have a 5 tuples: state, previous state, input symbol, new state, write symbol, and head motion, all right? That's 5. 5 is enough. That's the beauty of Turing machine. Then there are other variations. Turing machine, you may have both sides infinite, like word, right? Word is infinite, left, right, and up and down. Same Turing machine. Multiple tape Turing machine, all right? You don't have to have a camera. You may have a microphone. Same Turing machine. Non-deterministic, all right? Because Turing machine is symbolic. Transition is deterministic. Non-deterministic means that it depends on property, probability. And same thing, right? Non-deterministic, like a guess, like probability, same, equivalent. So once you have a probability or uncertainty of AI, it did not change the story, right? Universal Turing machine, same, Turing machine. But you said, I'll get to the universal Turing machine a little bit later. What's the difference? Universal Turing machine means that you start to code the information using a language. That's the beauty, all right? So that we still have a human learning, we have a human language, then you start to use the code as a natural language as a code. That's universal Turing machine. And then become general purpose. You said, no, our computer did not have a universal language, and we have a computer language. So computer language play a role of a natural language in special purpose computers and our general purpose computers, all right? So now universal Turing machine as a general purpose machine, I get to that, all right? I'm running over time a little bit. I will stop, have a break very soon. Sorry. So now, universal Turing machine, that you have a program as input. In program, it's coded, and the data for the program to apply, it's also coded. So the input is not just data, not just classifier. It is a general purpose. Why? Because I'm input a program. And a program could be written by anybody. Then I have a language that's called 5-word sentences, 5 sentences, and it's a universal Turing machine UTM language designed by Alan Turing, and that's like our natural language. It's like our C language. It's a general purpose because Alan Turing proved it, all right? But it's sufficient to prove that you start to use the understanding of this universal language, 5-word sentences. You can do anything that program wants you to do, all right? So simulate the program on the data, output the result of that program on the data to the tape. That's how we can have general purpose computers, right? From your laptop, from your desktop, to the supercomputers, or to your cell phone. So learn it. If you don't really get the detail yet, you must learn it, right? Because the revolution is already started based on universal Turing machine. So the other Turing machine, you have a special purpose, all right? From data to the result, all right? You program it. Universal Turing machine is somebody else program it, all right? Then you read the program in the data, then you program that operating system, basically. The operating system can simulate any program on the data. So it's a general purpose. That's the beauty from Alan Turing over 70 years ago, right? Now, but once we have computers, our symbols are falsely grounded. We have ASCII code, all right? And we have vision, but vision are falsely grounded. So ImageNet is falsely grounded. Then with neural networks, they are not grounded because we have a network like Hava Siegelman. She's a good friend of mine and I respect work. She was probably the first one that using a network to, it's not learned, it's hand-mapped neural network to simulate a Turing machine that handcrafted, right? So input line are symbolic because if this valid is 1, then symbol's there. And if 0, it's the symbol's not there, only single symbol, all right? It's not the image, right? But her work was cited in my machine, in my paper, right? Now, there are neural networks falsely grounded. Almost all neural networks are falsely grounded, right? And now, first we have post-selection. I'll get to a little bit more, right? Using test set, right? Human does post-selection, right? Machine does post-selection, right? Human does post-selection because the human are using open skull. Machine post-selection based on fitting data, right? Give example, there are neural cognition, CNN, HMax, SVM, LSTM, and etc., etc. All right. And DN did not do that. DN only one network for each life, only one network. All right. It's the only network that you see that only one network, only perception, and over here. All right. It's the only network method because perception grow a single network on the fly. All right. Using similar idea is like once you new feature, you copy the feature into network, into a new network. All right, as a brand new, no, I'm sorry. Once you new feature, you copy to a new neuron. Right. The control of a Turing machine is a finite automaton. Now look at these 5-word sentences. It's too complex, right? And we redesigned it using the proof so that you will output the actions and output the state. Then it becomes an FA. For this FA, it's like a new state, a new input symbol, it become new state. That's FA, all right, published in 2015. And then FA is handcrafted. In the symbolic AI is handcrafted. And then we have a traditional AI. We have a search algorithm using symbols. And simple is useful for search, but it's bad, all right, because it will not be able to use for neural networks. So like Dijkstra algorithm, you have A*, you have CNN, you have Q-learning, they are all doing search. And the time is up. And I like to have a little long break. And now let's break 5 minutes. Now it's 8 minutes. So we get back 12, right? So 3 minutes. Right, so let's pause recording. So let's resume. Now talk about developmental networks. There are many details. Even people that have taken BMI course age 71, at the end, I have a PhD student still told me that they really still don't get everything. That's very natural. They are really honest. So many critical ideas in the developmental networks. So you don't expect that you can understand it totally. But the tutorial is just give you more time than a paper. A paper get like 15 minutes or 20 minutes, and you will not get the enough ideas, all right? So I give you some snapshot ideas so that you can get motivated to learn more, all right? So I tend to use more theory in this tutorial, different from my previous tutorial. I started with more like ideas. But I give you a little more theory so that you know understand the theory is extremely important. Those people that did plagiarism and fraud, they did not have enough background for theory. All right, although they have education in the United States. United States has education is pro and cons. All right. Pro means that they rely very much on the autonomy of the learner, and you can demonstrate the skill of problem solving. But in the United States, there's lack of training of basic skills. So I get both of the buzzword in China, and I have a chance of being solidly trained in China. In the United States, has a flood of new ideas. Somebody please mute you because there is some sound coming up. All right. Then one theory here is maximum likelihood. Because you have local minima, how do you deal with local minima? You must have optimization built in so that when you do optimization on the fly, you solve local minima issue. All right. So for the brain, number of neuron is 100 terabytes, neurons. Then the content input, you have X as pixels, you have Z as action motor, muscles, and Y is a hidden neuron. And the number of neuron in the Y is about 100 T. And the neurons are grow incrementally in the DM. And each neuron, firing neuron will update, and not firing neuron will not update, all right? So it's the idea of competition, like market economy. And we approximate probability distribution as the Voronoi diagram. Extremely important, because you have competition, all right? Competition means that if I'm the top one winner, I'm the center of my Voronoi diagram. It's like I'm the winner of the vote from the population. So within the diagram of my Voronoi region, I will not assume that distribution, all right? There's no distribution assumption. I have somebody that was meeting me, and his answer was that, oh, we probably have a mixed Gaussian. Mixed Gaussian is garbage, I tell you, all right? You should not assume any distribution. And in our case, our distribution free. We just have a competition and within the net cell, Voronoi region, because you are the winner in the product space. In 2D, we call the Voronoi region. In the product space, in the unisphere, and it's a Voronoi region. We still use the term called the Voronoi region. Then inside Voronoi region, you do minimum variance estimation. All right, you still do not have a model of distribution. So a high dimensional space, 100T, and we get global optimality. So we do the minimum average distance from voters to each neuron through the competition and through the minimum variance estimation, right? We don't have any distribution of the, any assumption of the distribution, we don't, all right? Because we have competition, right? Now, first of all, I talk about a little bit how you can develop features, all right? PCA, some people even after teaching, they probably still did not get it. PCA did not have class label, right? It's unsupervised method. I have data there, all right? And I don't have labels, I just have data, all right? I suppose each data corresponding an image. Then the PCA will use the variance, expected variance, to estimate the cloud, the long axis direction and the length, and the second long axis and the length, and the third long axis and length, and so on. Beautiful math, all right? And very useful for as a starting point to understand how neuron can find features, right? So then we need to do CCI, right? C for candid, C for covariance matrix, I for candid, covariance free, because we need to compute the principal component without using covariance matrix, because we don't have covariance matrix. It's too big, all right? Number of pixel, covariance matrix need a number of pixels squared. It's not possible in the brain, all right? So we need to estimate the covariance properties without getting covariance matrix, I for incremental and the PCA, all right? So once you have each neuron was estimated its weight, that's using incremental average. Then once you have a new input, we estimate the mean using incremental learning. You see that incremental means that this learning rate, this retention rate. If you add these two, you always equal to 1. So the energy will not explode. That's the candid part. Will not normalize the input vector that corrupt the energy, because energy is important in the competition, all right? Then this is the average incremental computed. Then the new input coming in, and then you take that difference is called scatter. And what do you mean scatter? This is the average. And because I don't know the center, right? I incrementally compute the center, then I compute the scatter matrix, all right? Scatter vector. So this is scatter vector. This is the scatter vector from the center. So scatter vector is always from the center, all right? So U is a scatter vector. Then we incrementally compute the PCA. Now this is like a magic, but if I were you need to review the details of power method, all right? And go back to original paper, LCA paper. And this is a response weighted input. And we need to normalize the direction. This is the direction of the vector. And this is the input. Then this is the response. And then the response weighted input. This is like Hebrew learning. Then the learning rate, retention rate, previous weight, new weight. Then you use the idea of incremental learning. This is the retention rate. This is the learning rate. But retention rate is 1/A, T for H and num. And retention rate is a little bit larger so that you can rely on new data using larger learning rate than normal, all right? Then you compute the next scatter vector, all right? This is the PCA, first PCA. And this vector is used for the second PCA and so on. So this is a projection of the remainder residue. Then this is the new orthogonal component that's for the next PCA, because the next principal component, we know they are orthogonal. If we do not compute the projection, then you will not be able to compute this vector, all right? The next V, right? I is the first, start from first. So this is a very beautiful method, very fast, and guaranteed convergence. So DN1 algorithm is basically we will drop the orthogonality of principal component, because look back, right? There is the first principal component, second principal component, they are orthogonal. And we do not need that. Brain does not talk about the orthogonality, all right? Brain, using biology, they did not do that. Brain did not do projection, right? As far as I understand it. There's a little bit too much for me to talk about why. You look at biology. Biology does not have this luxury to do that. This is too much, right? So we use the DM that start to use each neuron will compute the first principal component only, are they called neurons, right? And each neuron has a weight and it has age. Then what it does is each neuron has a bottom-up input, top-down input, and the other parameter of the network. Then this is the function of the neuron. Then you update your network parameters and you compute your response, right? And each neuron with competition, and every neuron is doing competition in parallel. And we compute the response using unified inner product, right? And we unify the bottom-up input and weight vector. We unify the top-down input, and we unify the top-down vector. So each neuron has top-down input and bottom-up input, because the top-down input, I will get to that later on, is the context, right? And so far, I didn't see any other neural networks that can deal with top-down input as we do, right? They're all doing feed-forward. That was wrong. You must use top-down input, right? Then you have two components, and inner product equal 1 means direction perfectly matched, all right? So if you don't do half and a half here, and the maximum is 2, minimum is -2, and that's the value you do competition. You have C neurons, you do competition, and then pick out the winner, right? That's a computer method. How brain does competition? Brain does inhibition. I'll do that later on, all right? This model is simpler to understand. So we have a lobe component analysis, LCA. We drop the orthogonality restrictions, and the interaction between the neuron is first is the electrical inhibition, right? And we keep the CCI part. Graphically, it's like we have neuron, they do competition, and in our network, competition is realized as a top K competition. Later on, we have a more complete competition later on, all right? Then we have an input. The input has bottom-up, top-down input, not just one type, all right? Then the neuron, winning neuron will fire, only have one winner, all right? So graphically, you can see that we have clusters in the top-down space and bottom-up space. We have 2 components. Then we can have vectors. Those vectors are samples, your living experience. And we want to partition that space into C regions, C vulnerable regions. If we have C neurons and use competition to find winners, and the winner will get vote from new input and update its center, all right? So the lobe component is the principal component of region I. So we have a C lobe component. That's the idea originally from perception. Perception will initialize every neuron based on new input, new feature. That's too wasteful. Now with this one, we based on the we have a sensitivity test. All right, if the inner product is larger than certain value, and we don't have an existing neuron to take care of that input, then we spawn a new neuron. Then our spawning is slower, all right? Slower, not as fast as a perception. So then we have different normalization method. The last one we have here, that each component is normalized to maximum 1, or we can normalize the Euclidean norm, and we can have each input has a positive, negative, then it becomes something like that. A center is over here, that each component has positive, negative. And LCA was published in PEMI 2009. And I would suggest you read the paper that there are some detail there. And LCA is duly optimal, right? What do we mean duly optimal? The target is optimal because we have theoretical target to find the lobe components over the huge space, all right? That the top-down, bottom-up input is huge dimension. It corresponding number of pixels corresponding to the number of pixel plus number of muscles, all right? Huge space. And we do incrementally compute, and those V's are the vectors of lobe components, all right? And those are the optimal, and the target is optimal. But we never had enough to compute that theoretical expectation, right? We never. So we have only samples. The sample comes in incrementally. So we need to update optimal one sample at a time. That's a step size. How much? We automatically compute the step size by using our incremental average idea. So the direction is the best because I'm moving towards this star, although we don't have all the samples. We only have n sample at a time. Then we have new sample comes in, we move in the right direction, and we step size in the correct amount. Then the duly optimal. I repeat again, the theoretical target is optimal and the step size is optimal, all right? Duly optimal. So intuitively, if you have a non-optimal one, then one sample comes in and your weights jet around like that, all right? And our PCA or LCA will jet around a little bit, but the smallest possible, all right? In term variance, variance is smallest possible. That's efficiency. The estimator has the minimum variance. So the jittering is the minimal. So in other words, we cannot avoid error, but our error is the smallest in statistics, right? So then when we do top 1 competition, we can move up to top K competition. So the competition is like if we have 1 winner and the winners too few, we like to have a K winner. So the K winner becomes the committee, right? So the top-down match, bottom-up match, and we find other K, and those are the winner committees, right? And then the end learning is hidden, all right, because the winner will not will update and loser will not, all right. Then this is very similar to our PCA, all right. And theoretically, we are computing the V's. Those are the batch estimate of the response with the input. Although we cannot compute it in a batch fashion like that, we compute incrementally in that fashion. Brain cannot do batch learning. So maximum likelihood optimality of emergent Turing machine because the network will end up with approximate an emergent Turing machine, right? So I will talk about Genesema later. Genesema is also it's 8th property of a system, and it's also the company's name, the startup that I created. So if you have sufficient neurons, then the Turing machine emergent is error-free, right? But for any finite number of observation, the network will learn a Turing machine that's error-free because you have enough neurons. Each neuron will represent a transition, all right? It will memorize the transition. If you don't have enough neurons, all right, then start to do minimum variance estimation or maximum likelihood. So now I'd like to mention a little bit more about the theory. Theory is extremely important, and no other network has such a rich collection of theory. The first one is that, as I said, that the control of a Turing machine is the DM. It approximates FA. Now, give a nutshell. Suppose I have a FA, right? State, input, go to next state. Meaning double E guy understand that one. We get rid of symbols. We change that one to vector, change it to the vector, vector. So this equivalence means that the vectors will correspond to symbol. And why it's good? Because this is handcrafted. Vector is emergent, right? This emergent from muscles, the emergent from pixel. And the muscle and the pixel come out on the fly. You say, no, how can you do that? How come muscle can come up fly? Yes, like you ride a bicycle. You don't know how to ride a bicycle, you just tried it. Our robot just tried it, right? Try your muscles. Although you may make mistakes, but you are learning on your own, right? You don't need your mother to give you symbols, right? And then from symbolic search to neuronal competitions. So instead of match of symbols here, right? It's a dead end, all right? Now we have competition that this can be done inside the skull. You don't need your mother inside the skull, all right? So every neuron will do competition. And the DNA theory from our paper is that Turing machine is an FA. That's a symbolic, all right? And then if we use vectors, we become emergent FA, right? Then using probability distribution, some people probably were not really, including Jeffrey Hinton, and I think he's an honest scientist. Jeffrey Hinton in the YouTube interview, he said that when he was in the school and he was not really best in linear algebra. If you are not good at linear algebra, everybody, you need to refresh your linear algebra, right? Refreshed it, right? And now you are motivated, all right? Before you probably not sufficiently motivated, but I was, all right? At that time, the Chinese government taught us that we should do something to contribute to our motherland. So my exam is for me to take the skill with me for my life. So I memorized all the proof. No kidding. I memorized all the proof so that my proof skill, I think it's reasonable now, even when I get old, right? So the DN and Turing machine has matched. Sufficient neuron is error-free, insufficient neuron, you have optimal. That's you prove based on distribution. Many people probably say, oh, I don't know how you can prove optimality based on distribution. There are 4 kinds of distribution proof, right? Minimum variance estimate. You have convergence based on distribution. You have convergence almost everywhere, right? And 4. And you want to review it. These 4 kind of convergence based on probability. Then the 4th one is based the way I just the 4th one is convergence based on probability distribution. Right? 4 kind of distribution. You want to review it, all right? And then our proof is based on minimum variance estimation. All right, we don't assume probability distribution. If you know the distribution Gaussian, that's one story, but we do not assume mixed Gaussian, right? So it's logically complete, and like a universal Turing machine, because universal Turing machine is a Turing machine, right? And we need to talk about motivation later on, because if we have only logic here, you have optimality. But without motivation, then we will not be able to do anything, right? I have a complete logic, but I sit there without doing anything. So you need to do motivation, and then we do so that we can do self-programming, right? I'll do that later on. So what do you imagine is SMR, right? I will do that later on, but I use that first so that you get the impression, all right? So to summarize, DN autonomous learn any Turing machine, including universal Turing machine, to generate a grand Genesema universal Turing machine inside it with the following two properties: add a free sufficient neuron, and if you don't have you learn out the neurons initialization, then you becomes maximum likelihood. All right, then we got more detail about the DN now. We talked about LCA. We did not talk about the other components and how you can ever have a universal Turing machine, right? First, talk about the APFGP, auto programming for general purposes. Right? Suppose we have a human being, right? And he can do math research. Can machine do the same in the future? Yes. Without theory, impossible, right? Because human will pick up the topic on the fly, right? Give example, algebra in this case, right? And even the numbers on the fly, right? And draw diagrams on the fly, do reasoning on the fly. APFGP must be the central topic of our future AI research. And inside skull, and because it must be closed, and your programmer cannot peek into it. All right, throughout the life, from the first life, and outside skull, nature as a teacher, including human. For example, you as a teacher, you can interact with the robot through talking, through writing, all right, through class teaching, but you should not open the skull of the student, right? So why APFGP? All natural intelligence uses APFGP, including human, horse, monkeys, fruit flies. And all the biological life, you have lifelong experience from a single cell, zygote, right? Zygote is the cell from your mother and father, they get mitosis, become a single cell. That's how your life started, right? Then you have embryo, you have fetus, then you are born, you have infancy, you have adolescence, you have adulthood, you have your senior age, then you die, right? And the behavior becomes increasingly low-like. Your baby probably did not show much low-like behavior, but later on, your baby start to talk to you, they start to have a sense, then they look like low-like. So graphically, that's not including before birth. By the way, I couldn't find a better diagram, all right? It should be before birth and after. Then the autonomous programming, you have two modes. One is learning from teacher, but skull closed, right? And this is a supervised. And what do you mean supervised? Supervised, in this case, is that motor is supervised. It's like your muscle is supervised. But your mother cannot supervise your everything. Like your mother cannot supervise your vocal tract. Your vocal tract is totally autonomous. Your mother cannot supervise your tongue and shape your vocal tract to pronounce your sound. That's why deaf means what? Mute. In human, deaf means mute because even you can make a sound, but you will not be able to talk like a human because you do not practice your muscle. So if your method can deal with that issue, you are on the right track, right? Mode 2 is learning from real physical world without explicit teachers. Explicit teacher is like you can have a class, you take a class, your teacher is explicit teachers. But You discover from the real world. You don't really need a teacher, all right? Like Newton, right? Like Albert Einstein. They don't need a teacher to discover things. They self-supervise themselves. In other words, they do by try and error. And I will talk about later on, it's called imitation. Try and error is not totally unsupervised. And every discovery was from imitation. They do what they think is the best try. The best try is imitation. I'll get to that towards the end. So conscious machine through APFGP, I mentioned 2 papers. There are more papers. I would mention others later on. So this one is APFGP through conscious learning that was published in a archive. But the real publication is ICDL Epiloba 2020. Unfortunately, I have another paper talk about the other concept of conscious learning, so the better understanding, and I have theorems, but the ICDL conference 2022 rejected, so I will not be able to talk about this material. Life is tough. So grounded symbolic learning, Turing learning, basically, that instead of have tape, now you have pixels, you have muscles. And you pay attention to, instead of symbols on the tape, you pay attention to receptive field in the image. Then you have vector input. You have vector input from vectors. This vector could be from your body. It's like you are riding bicycle, for example. These vectors. So I have some collaborator here, like Professor Weng, right? Professor Weng was doing robots. And the robots, your controller, you have muscles that controller can self-supervise yourself. Then you grow your hidden areas, right? Then you have pixels, you have muscles, you grow a hidden area. So in this mode, you should not have a task-specific machine. You should release your robot. That's our Dave robot. You release your robot to the world, all right? Then he will learn autonomously, totally free, right? And interact with your robot through sound, through information. Now, what happens, and this formulation is extremely important to understand. Otherwise, people say, I don't understand it. It's just too much. So, nutshell, you have FA first. State, input, new state, new input. You unfold in time. Unfold in time is the keyword. Because once you have to FA, you see the diagram we had before, that was bad. You will not be able to understand the time released part of it. We make that one in this time release part. You see that input, input. This is one time, this is next time. Time unfold. That's a new representation that I came up when I doing research, because it was too tough for me to explain to our reviewers, because reviewers reject our papers if we don't write clearly, right? Then I've, instead of symbolic transition, we have vector transitions. Then we become symbol free. Then this model is not time unfolded, and we do fun unfolded. Z, X, Z, X. Then this is time 0, 1, 2, and I add new things called Y. Y is the inside the skull. You say, why we do need this Y? We don't have Y here. We don't have Y here. We don't have Y here. Why do we need a Y here? I was asking that when in the class. It was difficult to answer, actually. Because we are doing vector mapping. The vector mapping, you must have internal representation. For symbolic mapping, you don't need internal representation. All you need is just match X, the sigma and Q in the lookup table. In the lookup table, you don't have internal representation. But in our network, you must have internal representation. That's what the brain is for. Brain uses internal neuron as lookup tables. Lookup table is symbolic. Our neuron is vectors. So you also need to have a neuron, internal neuron to new internal neuron. Y-to-Y transaction is tough, right? I have a hard time to work with my students, but they are genius. They did very well. But originally they start very quick. They grow neuron very fast. No. You cannot grow neuron very fast. Your biology does not grow very fast either, all right? Because otherwise this is new. How can you figure out that this new to new transition very well? So this must grow very slow. This came in quick. Y-to-Y is slow. Remember, Y-to-Y grow very slowly so that you have experience that's sufficient for Y-to-1 mapping, all right? So you do slowly. Okay. Then this diagram is truly important because I'm including time and including the word. This is the actable word, all right? That's a sensible word. Then you have Z, Y, X. They have 0, 1. That's our discrete time. Discrete time is much better than the network represented by derivatives. You probably don't like me, but I try to give you my biased idea. Don't use derivatives. All the neural networks that the derivatives, you get nowhere. Why? It's a trap. You get stuck. Because derivatives is like difference, difference between the columns. And you take derivatives, you lose time. And they're not exact. But if you do difference in discrete time, you are exact. Then we have optimality. That's why all the neural network guys that are doing differentials, they never have idea of discrete samples. They never have a problem of global optimality because their tool is like Newton. Newton already used derivatives. By the way, derivatives is good for calculus, but not for neural networks, right? Because our computers in discrete time. Don't use derivatives. Don't use linear rule based on derivatives, right? Then we have this unfolded time. That brain goes like this, and the word goes like this. So here you have your mother, your father, your classroom, your friend, your classmates going on, and you have your muscle, you are walking, you are teaching, you are singing, and you become more logic. And this diagram is very important. People say that how do you link with symbol to this one? And when you have many passes going on in the brain. So your Y, each column, you can only take input from this column. This Y neuron or any neuron here cannot take input from the same column. Why? Otherwise, you can wait. Neuron cannot wait. Neuron must do parallel computation. I'll get to that later on. All the neuron must do parallel computation. You start to wait, then you don't have a parallel computation. Then you get stuck. Because your network is not parallel, all right? And we have a parallel, and this column take input from this column take input from this column. So Y can only take input from X. Y is X, and Y make it the Y, but I simplify. I don't use Y here now. But this Y can go to Z. I drop Y to Y transition to simplify the network. Then you can see that for X, your image input, to get next Z, you need the 2 iterations. 1, 2, you get to that. You see that? You need the 2 columns. Why? Because X is not directly connect to Z. The X from pixel, you must go to the brain first before you get to your muscles. So you need the 2 iterations before the input can output to the here. 0, 1, 2. And there's another thing going on because the Z will be updated over here too from the Y. So Z is the context. Z is the context. In this case, Z could be similar to Z. So that this Z is interpretation of this Z and this Z, right? And I use the 0 here means that if this transition is new, then you don't have any output, but your body will supervise yourself because these Z are smooth. Your muscle has mechanics that allows you to follow the momentum, all right? So your body becomes smooth. You self-supervise yourself. Now then we can auto-programming, right? Then you have multiple tasks, all right, or purposes, here T1, T2. And later on, we'll talk about the what with consciousness. You need a purpose, all right? Without knowing purpose, you don't know we are doing well or not, right? Give example, right? And so you have a purpose or task I equal to 1. Then the auto programming, you start to learn tasks, all right? Give example, you start to learn alphabet, A to Z. Then you start to learn simple words like cat and toy. And you gradually, you learn how to go to school. You can learn in Chinese, you can learn English, or you can learn the C language. Then you can start to program in the C language. All right, our robot should be able to do programming for all the tasks it learned using computer language, right? And our robot should be able to learn tasks on the fly using our developmental networks, right? So I still use the symbol a little bit. You can see how symbolic takes place. Suppose I have a FA. You can consider this like Turing machine, and this means accept. All right, this means not accept. Single circle means not accept yet. Then this is a transition table for FA. From B state with 1 input, then you have a next state is B. And this symbol, I have 4 symbols. And as an example, I make it short, all right, only 4 by 4. Then next, I will get rid of these symbols. I use muscles, 2 muscles to represent the state output. I will use 2 pixels to represent the sensory input. Here it is. So I cannot use symbol here anymore. I can only use muscles. I just transit from A to 0, 0, C to 1, 0, and so on, 2 to 1, 0. Those are the binary pixels. Those are the binary muscles. Now, do you think this is a lookup table? Yes, this is still a lookup table, but it's not symbolic. And reading this one is tough. Reading that is easy, right? But brain does this. Brain does not do that, all right? Now with that one, you need Y, right? So let's do Y. So I have that one, and I have a Z, 2 muscles, X, 2 pixels, and I need a Y start playing. And the first Y means that I have this is the first input. I have a Y, first vector. This Y will remember this pattern, all right, called Y1, all right? Then to represent this transition, 1, 0 will come to here. See that? 1, 0 will come to here, and the next image coming in, and I have a second Y initialized. If they are the same, this Y will not initialize a new neuron, all right? If they are different, we initialize it, or they are sufficiently different for DM, you initialize a new neuron. Then you go to 1, 0, 1, 0 will come here. Hey, come here. This next image comes in, and keep doing like that. You see that? This is very, very clear. I repeat, very, very clear. Those reviewers reject our paper, they should follow our literature. All right, please follow our literature. That's not something that you can still ignore, right? That's your life, right? Reject our paper, not big deal to you. It's a big deal to science, all right? You act like a church. I repeat, you act like a church to Copernicus. Then the comparison among the machines, and we are the only one that can do auto programming, right? General Turing machine. No machine can do auto programming for general purposes, right? Whether you talk about Turing machine, you talk about universal Turing machine, you talk about robots, you talk about applied neural networks or deep learning, you name it. They will never be able to do auto programming for general purposes. And our is the only one. We have not demonstrated on the robot yet, but Xiangwu and Zhejia, they already demonstrated through simulations, all right? And great performance. Now, I'd like to give some graphic explanation, right? Some people just say this one diagram. This is showed at the IJCNN in Alaska. Some people were asking, the only new one here is the muscle, not only one. This is a good question though. He said muscle as input is new. Yes, but not only one. All right. He said, is this the new one? Yes. Neuron has input, not just from bottom-up input, like deep learning, right? Like Alex network. No, you have a context as input, all right? The context is the state. The state is not symbolic, but your muscles, in this case, muscle could be what and where and the scale, how big that is. Or could be other things, like natural language, like my talking. All my talking, my muscle contraction is state. That's muscle. So my muscle need to match. So muscle will change which neuron will match, right? Do you see that? Because each neuron, you have two parts input, all right? And the same neuron will take a smaller receptive field at different locations, and the same neuron will pick a global location. So global location is like setting. What's the current setting? Is the street scenes or it's a beach scene, right? And here is like, what's the context, right? And then you have a top K competition, and the winner will, in this case, if this winner will win the global competition, so you are looking at the global view, all right? Attention is not always local. I repeat, attention is not just local. Attention could be local and global, and could be different locations too. The next time this neuron win, and then you pay attention to this local view, and you pay attention to this context, all right? Because this context is time correct, right? Like that. But if you do symbolic network or you do a Markov model, you get stuck because the feature, although are pixels, you turn into ABC features, and ABC becomes symbolic input. Then you have state alpha, beta, gamma, delta. They are handcrafted. Then you start use a Markov model to represent the probability. Probability is junk if you do symbols. Why? Because symbols is already brittle, and you do not have enough symbols, and the brain does not understand your symbol because machine does not understand your alpha, beta, gamma. Do you think this machine understands alpha, beta, gamma, delta? No, they don't. All right. And uncertainty represented by this probability is only a gimmick, superficial, not powerful enough. This machine will break no matter how many you have here. So Google, no matter how many gamma, alpha, beta, gamma data you have, they have billions. Still brittle. Why? Because the machine had no idea it's not doing well. All right. You never be able to exhaust all the symbols. All right. Human does not have enough symbols. Right. I'm giving you a writing bicycle. How do you know that you have enough? How do you know that you have enough symbols? Human, the body language is much richer. All right. So that's how it learns. This is for vision, but it don't have to be vision. All right. Could be cochlea, right? Could be cochlea. Or could be muscles, so that you start to do exercise, body language. And people said that vision is hard, right? So in the context, so we enrich the Z to include the long-term goal and where and what and scale and GPS. Then learning through time, and the red part is active part. And you should be able to pay attention to different parts of the object. You see that? And they look very complex and very simple for a child because those are going on in the skull, and it's simple for DM. DM is simple, all right, because it's mechanical. Then what happened to the segmentation, right? And I'm doing this simple things like here, right? It's a rectangle, but in the real world, we have a synaptic maintenance, right? So suppose you have a square object, including the square, and this is B is the real contour of the object, and this is the learned contour. And our synaptic maintenance is able to cut off those areas, all right? Suppose the neuron start with a square like that, because deviation match from these areas are high because background may change, all right? This time I'm the winner for this pick, but next time the background may not be the same, right? Because object moves. I'll give you an example. Suppose the object moves, right? The object may move, foreground, and background may change. So my background may change when I win. So when I win, the standard deviation of these pixels are high, then I want to remove them, all right? So the synaptic maintenance will remove those pixels so that my receptive field becomes exactly or close to the real contour. Do you need a teacher? You don't. All right, you don't. And the contour are automatic. So then you have different objects, right? You have different lightings. You don't have the same lighting though. So lighting will be shared by different neurons, right? And the competition will take care of the sharing, right? So the transaction I had before, and the network, this is the web network that you have like, this is the muscles for locations, all right? This muscle will tell you pointing, which part you are pointing to. And this is your vocal tract. You will take type A or type B, all right? Or for baby, it's a sucking, all right? Sucking, this means like milk, all right? The muscles, they are all muscle, but those muscles are for different usage, right? And those are our language like relationship, and the probability will allow them to do a synaptic maintenance. They will connect it to the different region. This is occipital lobe, this is a parietal lobe, this is a Weng pathway, this is a temporal pathway we call what pathway, right? Ventral pathway and the dorsal pathway, and this is the where pathway, this is the what pathway, and that's qualitative, all right? Not exact, in fact, incorrect, but it's good approximation in neuroscience. Then once I see two parts, I have two neuron firing, and I have two position firing, and which one win? It depends on competition, because we have a competition in this area, competition in this area, and I happen to pay attention to A, I happen to pay attention to B. If the context is correct, I should look at A. Suppose I'm supposed to look at red objects, then I look at A. If I'm supposed to look at a blue object, I will pay attention to B. That's object detection, all right? Everything determined by the context. Then classification or detection or segmentation takes place at the same time, right? Good time for the second break. For those who would like to stick around, I can answer some of the questions, but will not in the recording, so that you can feed. Now, before we have only where and what, right? We did not talk about relationship. And maybe I would talk about conscious learning. It will become really really more complex. Give example, even including figured out why China became a developmental country because of geography, right? Whether you agreed it or not, at least one factor, one major factor among many is geography, all right? So it was difficult for China to move ahead to catch up with the United States because United States has different geography, different history, all right? So how does that happen? It's a relation. So suppose we have two objects, A and B, right? And A play B, or A, B gave B to C, or United States is located in North America, and the United States used to be a colony of UK, and UK is island in Europe, and Japan is island in Asia, something like that. They are all consciousness, all right, can be represented as a natural language, but it does not have to be natural language, right? Could be like riding bicycle, all right? Learn how to aim a target using a gun like that, like swimming, and how duckling, given up how duckling learned swimming. Much of the behavior was inherited, of course. In the paper, I'll talk about imprinting. Imprinting means that how you generate initial behavior from the wide behavior. But the human imprinting, very little, almost none. Lower animal has more, like duckling will follow anything that moved in the first few days, then a stop sign moves and duckling will follow a stop sign, right? By the way, stop sign is not a symbol, it's an object, all right? And normally a duckling will start with a moving sign, and those are their peers or their mother, right? And at the end, automatically builds knowledge hierarchy, all right? And that knowledge hierarchy is through the linking. You see that? So give example that if A and B, A or B becomes two symbols, this neuron will have input from A and B, and if you have this relationship P and Q, and that P and Q will relate it to the N and B, right? Just like A plays B, now we have three, A and B. A gives B to C, they have 1, 2, 3, 4, you have 5 objects. So the same thing happened more simple, and I did that AB, you have a neuron, that's, I unfolded so that you can see the hierarchy from low to high, but actually this area all in the same brain, because you have top-down projection from these like vocal muscles, and the AB relationship will project down into this neuron, and this neuron has a top-down projection, top-down projection, top-down projection. They are all top-down projection. They do not get the link with the bottom-up linking very well. That's very much like Xiangwu, the question. Xiangwu said, what about the scale, right? This is a large-scale neuron, right? Because parents handles large scale. And the scale is the, for this type, will cover all the positions, B will cover all the positions. So this will cover large scale, right? Because its parents has a large receptive field, and also has a higher projection from higher muscles. This is AB group instead of this only position. This is only position, and this is only type. You see that? So those are the earlier neurons, I call it. These are the later neurons, and all those wiring will be automatic. So I'm excited that this scheme should be able to come up with neurons that enable consciousness, because we don't have any definition of where, what, or relation. We don't. We have only muscles or vectors of actions that can act or make sound. By the way, Xiangwu did vocal synthesis using vectors in the motor so that it can speak. Now we have big data. why we should not use handcrafted features. I'll give example, very successful application. And I like George Hart, and he has a startup called Karma. And he has a talk that detect features, like this is the features, those are the edge features. And he did not talk about detail how he grouped it. He probably grouped the features so that you can check lanes, right? You start to form lanes here, form lanes. The problem with Karma is that if you are not tracking feature very well, for example, if the curve is too sharp in my real experience, then the system breaks, alarm sounds up, all right? Because it did not know how to do the lane centering task anymore. Because system did not know how to evaluate whether it's doing well or not. He cannot learn the place where you have a sharp curve because he cannot learn there. Either data is not sufficient, or the trainer did not provide a teaching example, or the trainer said that this is not something that George Hart told me to do, all right? Because otherwise performance will suffer, right? If you do a sharp turn, and other performance will suffer. So George Hart, I guess, right? George Hart that don't do that, right? Then the program did not do that. And did not do that, so always has a boundary, right? When the system go beyond the boundary, he did not know that I'm still doing reasonable or I'm not doing reasonable. So it totally hangs up. The system breaks. And if it's in a traffic situation, the system can introduce a collision to me. I can sue George Hart and his company. Why? Because there's no way for the system to do a decent job of evaluation. So the neural networks is not decent, graceful in the performance. We hope we do. Brain does, human does, right? And animal does, but not our artificially trained network. So forget big data. You must train in real time. You must allow the system to train while driving so that he understands. You need to tell the system whether it's doing well or not, why you said it's not, all right? And whether you have detour, and you also train detour. So now look at some applications. We talk about vision, audition, natural language, and planning and thinking. So people thought that, oh, autonomous driving, we have 6 levels, and now we have level 1. And level 1 is still, level 1 is very brittle, all right? Consumer Report rated Karma system, they called Karma 2, all right, number 1, all right? In terms of the lane centering and lane change. And lane change, they did not do anything about sensing. Basically, they just move beyond to the left or right lane, basically, all right? The system is still very brittle in the sense that the system cannot evaluate. They cannot evaluate the doing well or not, right? It cannot really have a graceful degradation. And they just totally cannot, and alarm sounds up, all right? If the human is not there, you have collision, right? For example, in this case, we'll run into that person. Because you cannot just, you don't know what time the lane tracking works or not, because there are so many objects there, and there's no way to do level 1 well. I'll let you know. That's my prediction. We will never have a system that do level 1 auto driver assistance system well. So there's a plateau for even Karma 2, which use vision, which is right? If Elon Musk is there, Elon Musk, it's wrong to use the range sensor for scene analysis, all right? It should not, just too expensive and information published. Vision is cheap, but processing for vision is hard. And we must do conscious learning. That's my message for Musk. So we are doing this. It's a small startup called Genesema LLC, Limited Liability Corporation. And so the human see what the machine see. You have a stereo. And the human also sees signals that machine sees. And the action was taught through joysticks, right? And this is our student MSU company team members training system, and training is real time, right? At least in principle. The problem with us at that time is the speed of learning the image learning algorithm, or DM, on the cell phone here is too slow. I'll get to that, why we need a chip, right? It's too slow. So we have a small network that learn in real time that teach the object type and disparity, but still not fast enough. And we have a disparity learned, the real-time analysis, real-time learning. And by the way, the speed is real time, but we still collect the data though. And but learning is incremental using a single network. We only train a single network. Then this is the error through time. And this we have hundreds of frames. And it's we don't have problems like huge error and go down the gradual like that. But we rather starting from reasonable error and stabilize. This is the disparity. This disparity error is about 1 pixel, a little bit over 1 pixel. That was better than expected, all right? And this is the amount of top-down projection. If the top-down projection has more, then the system are not very responsible to the immediate input. But if we are learning natural language, because this is probably more important, all right? Because natural language context becomes more important. And for disparity detection, it more or less it's a smooth navigation issue. So disparity does not depend very much on the context, right? The context is in the Z. Now this is another project by Zhe, and he did PhD, and he used stereo cameras, and he used also long-term planning with GPS. So we don't have a consciousness in terms of the what global location you are doing. We use GPS, right? With GPS, then we start to use local environment, use cameras, and automatic integration through DN, and we learn skills from experience. We did not tell the system what do you do. We don't, right? We don't. We just take a baby out for a walk. Then baby sees those things. We have shadows. We have projection of the lamp post. We have a bad lightings, all those things, right? And all those are seen by the network, and including obstacles, lighting changes, and load edges. Sometimes you don't see load edges. Actually, you see that? And all your load edges is mixed with the shadow edges, and we take care of this automatically. So over here we have blue is the training, supervised training, and then this bright red is for use white to white connections. Then real-time testing is in this area. So this is disjoint. This is the training area, and are disjoint with totally disjoint term location. I was really impressed. If Zhe had a chance to watch this video, and Zhe is impressive, extremely impressive in experiment. And I said that when I tell him to go different section to do the testing, and I was concerned that probably he couldn't do well, and I was surprised, because those are different, totally different settings. Maybe camp sway, but different concrete types, different width, different shadows, different trees, different buildings. And I was really surprised. And he can get to that that performance. The performance is never, it never run into tree or ditch. And his wife is watching him. But he did not really kill himself. So in terms of recognition, you may have cars, you have pedestrian, you have signs. Signs are not symbols, all right? That are objects. And you may have distractors. My paper submitted to IJC in 2022 has to do with distractors, but my paper was rejected. I will not be able to talk about it. Sorry, that's a fact of life. And also need to talk about the goals, right? How you in lane tracking means what? How can you explain lane centering? You do not want to explain that only in the lane line, because in many cases you don't have lane lines. You want to also explain in terms of the other features like mailbox, like other cars. And then even just lane centering becomes a tough issues. So goal must be explained in our settings. So give example like parking, we have a vision parking, and we did not tell this is the parking issues, and we just teach the action of the cars and using vision only, Another is the work that conducted by Xiang Wu. Really impressed by Xiang Wu, and he's a vision guy, and with experience with at our MSU, and he was brave. He started looking at issue like Audition. Audition is not speech processing, all right? Speech processing means human speech. Audition including other natural sound, all right? So he was using phoneme to start with. I said, don't do that long sentences, because we start with phoneme. Maybe start with phoneme. So we may have multiple speakers, right? We may have vision, but we did not do lip reading, all right? We may have noise. We did not do much noise other than natural noise, right? And the sound runs like that, and very fast. In this case, about 20 milliseconds. Then you may have, in this case, you have two muscles out, all right? And suppose this muscle may have a type here, but type is so late, right? Do you see that? And over here, you don't have type yet because this phoneme may long last, all right? So how can you have label here, right? How do you label here? So label is from more detailed muscles, right? In this case, we define muscle in a final stage. It's called concept 1. Then concept 2 has a context from more dense actions. This dense action, that sparse actions. Sorry, at that time, we are still using label to label the two actions. But later on, Xiang start to use real voice synthesis without using label. And we must do it stage-wise so that we can build up our credentials. So the features for the cochlea, this is a cochlea. It's a 2.5 ton roughly. And for bass, that are responsive for high pitch, high frequency vibration. Because the biological property of the cochlea, and this is the higher frequency energy get really consumed. Here we have only lower frequency. That's something that a cochlea act like a band pass filter. So you have a low frequency, higher frequency. They are band pass. If you are interested, look at this curve. The curve is not very sharp, right? But it's a band pass, right? Then we learn from the model of hair cell, and those hair cells are cells that are located on the cochlea, and they vibrate when the cochlea vibrates, right? And we do not use capstone because that's handcrafted. there are some cell male frequency tuned for human sensitivity for frequency, but only for human speech only. And we must work on natural sound. So the idea is this is a newer work on 2020 by Xiang Wu and me. And basically, we have dense inputs. Dense inputs is like waveforms, and then desirable actions, that's motor area. And we are free of symbol in this word. And how do we get action, right? So we came up with the idea with a microphone, microphone to get the sound wave. Then we do PCA. We use this incremental PCA I talked about earlier. Then those PCA was muscle that drive this voice synthesis. See that? So they become loudspeakers that generate sound. Then we compare the difference between the heard sound and the generated synthetic sound from machine. And we ask human subject to perceive the difference between this and this. And we use a blunt test. And that's the work that very interesting. And the reviewer said everything's different. I really respect the reviewer that was such a difficult paper for them to accept. But finally, the reviewer accepted paper. This is a conference version, but journal paper was also accepted. One comment from the reviewer was that everything different because learning is on the fly and the synthesis is also on the fly. Not at the same time though, right? Because once you hear, you synthesize after. And for language, that's a work by Castro Garcia. His input has two kinds of language, English and French. At that time, we did not link with the Audition with the vector input from language. So we use vector, binary vectors. And binary vectors, each vector corresponding to a word. And we can also deal with other language like sign languages, but the principle is that if you link the sound with language, then you can deal with larger temporal waves. In this particular case, we use a symbol to denote sound. Suppose I say I don't have time, and I do not have time, and this is the same, right? And if we teach a machine to have independent, they called abstract, don't and do not have the same meaning here, then you start to have generalization because you don't have to learn each sequence differently because they have state equivalence, like here, right? And this is French equivalence. Je n'ai pas have not. N'aime pas. They have sentences in French. Here, young cat means kitten. They also have correspondence. And human does that, actually. Human does that, pick up short sentence first, get a meaning before they start to learn long sentences. So in our model, that you start with the, in this particular case, we have a particular input means end of sentences. So you go back to the beginning of the sentences. So we don't have to read the book. Otherwise, this task-free model must read the book. But read the book is too much for this machine baby, right? So we only learn the sentences, right? And so the period is the end of sentences. And we look at the some representation. We do have vision and audition representation. In this particular case, as a more intuitive for language, all right? So we map the PCA signal in the internal brain to a brain shape so that gives some intuition. It's like a projection into the 2D area. And this is the muscle coded by color. And this is another representation of the same muscle. Now here, the muscle here means meaning. Meaning is the context here. And this gray means that it's not a meaning, but Here is the language type. You see that? English or French or neutral. English, some context like number, all right, that does not have any language type. So over here are the context, and the context have different, each neuron, each neuron have different roles because have a top-down input, right? It's not just the neuron, it's like each neuron, wrong. You never have each neuron in the brain. You have a context-based neuron, could be motion age. Here, you never have a word neuron. You have a context neuron, right? This context in terms of the language type, right? Or language meaning. Here, the same neuron in the language type. So this is French in this context, green context, and green is right there. You see that? So our neuron never have a unique meaning in the bottom up because every neuron has top-down inputs, right? So not Schmidt cube, Huber-Wieser. Huber-Wieser have simple cell and complex cell. And if our work is right, Huber-Wieser was wrong, right? There's no edge neuron, no orientation neuron. It's only complex neuron with top-down input, right? So Nobel Prize, position cell, all right, also wrong because there's no position neuron. There's no pure position neuron. I get to that with more features. Like here, all right, we do not have a pure meaning neuron, but always context and bottom-up input, stimulus and motor, sensory motor. Look at the more complex tasks, you'll probably see more, right? Learn, think, and apply, right? So in this case, we have a robot start from here, and we take the robot for work, and it will move navigation first, simple task. Then once you get a target here, and we get reward, right? So the mix of the reinforced learning and supervised learning and autonomous learning. I'll get to the reinforced learning part later, right? And this is traffic light, green light, and red light, all right? Those are the obstacle, and those are the walls, right? And those are the sensors that has in this particular case, we simplify the experiment so that the pixel is sparse only when several rows, not very, that sees this kind of images, and those are detected color. Detected color is represented by color here. Right, and GPS tell you the long-term goal, right? So we don't have high level that can be figured out by GPS, and we decompose our training experience into classes: skill 1, skill 2, skill 3, class 1, 2, 3, 4, 5, 6, 7. All right, from simple to complex, right? By the way, our muscle in this example also use symbol as a representation so that we can present the papers. And then we have a FA that was in the mind of our teacher, in this case, Xiang Wu. Xiang Wu is a teacher. He has a learning walking forward, learning turning right, learning turning left, learning avoid obstacle, then more complex lessons, learning route 1, and corresponding cast, learning route 2, corresponding cast. Then here that teach it how to compare the cast. Cost is the value and the distance. Then these are the this is like a teacher Xiang Wu's teaching syllabus. All right, here's syllabus like that, but that's only in the mind of Xiang Wu. And then he teaches this baby, and baby start to learn from teacher, but baby did not have this kind of a design document in his capability to read about it, right? He didn't. So that's only in the design of the Xiang Wu. Then this is the FA, those diagrams are FA inside the DN's brain, right? Wiring is automatic. Then Xiang Wu tested in the new setting, all right? And the new setting turns out that baby has a new creative behavior. I refrain from creative terminology. I would say that's an invention or generalization or whatever. This it was not taught, right? It was not taught, and it was applying a new setting, and this learned baby is able to start from a new setting and does the task, and the performance is impressive. Performance 100%. And I talked to Xiang, no, this is bad because people, the paper gets out and they don't want to see 100% correct. Although our result is 100%, it's a new setting, it's a disjoint test. So later journal version, and this is a conference version, and later journal version, he greatly increased the difficulties and started with different positions like that, and also a more difficult setting. So he managed to show not 100%, so that our reviewers, respective reviewer, had a more chance to get this paper accepted. So now it gets to the most difficult task, right? It's called conscious AI and conscious machine learning from 3D to 2D to 3D, and I get to that. That's very heavy. I hope that it don't get lost. We have some people here already have taken my course over here, but I'm afraid they get lost too. But try to get the idea, all right? The idea first, so that you'll get a motivation to move ahead, all right? Think me like Copernicus. I'm saying that the Earth rotates around the sun, right? Or conscious is required for AI. You laugh at me, right? Just like Pope laugh at Copernicus. Pope did not have a chance to laugh at Copernicus, but Pope had a chance to persecute Galileo, right? And Galileo was forced to repent. He was put into, he was threatened to burn to death, and he was forced to write regret. Then he was put into house arrest. My time is better, at least that I just get a rejection. And I had a hard time to convince that plagiarism and misconducting AI is going on. It's not like in the old days. Old days, it just said that Earth is the center, right? That's the sun is not the center. Modern days, we have more researchers in doing AI researches. So many people, the good people, all right? They are doing misconducts. What's the problem? Problem is still communication, right? Communication means that we need to really respect truth, all right? We need to have scientific methods to verify the conclusion here is falsifiable. So you can prove my theory here or methods are wrong, all right? I'm not just saying that I'm correct. I just propose the method for you to verify, right? So we have a consciousness. Consciousness has been around for many years. Ever since we start to talk about natural intelligence. And recently have 3 major theories, and they are not algorithms, right? They are qualitative, right? There are so many. There is a journal called International Journal of Consciousness and AI. But I only mentioned 2 major ones. Ba is a neuroscientist. He has a book, very respected book. It's a theory called theater of consciousness theory. The idea is basically we are like a theater, and the active neuron is the actors are acting, and the not firing neurons are on the back seat, right, in the audience seat, and they don't fire, right? What we see is what's going on the stage, right? Roger Penrose, he is a physicist. I'm sorry that he did not know much about neuroscience. He never had any model about the brain, let alone neural networks. But he's brave enough. I respect his bravery enough. He said that the quantum phenomena play a major role in consciousness. He said the microtube in the material, in the nanoscale, is a major factor that we need to take into account for consciousness. And I think he missed the boat. I respect a scientific study that Roger Penrose did. He got Nobel Prize actually recently. But I'm not saying that Nobel Prize, everything is right, all right? Nobel Prize committee had a bad picture. They denied the Nobel Prize for Albert Einstein. And look at the interesting controversy around the Nobel Prize. And Albert Einstein didn't get Nobel Prize for his relativity, but only for electro optical effect, which is a really, really an interesting story for us to look at the Nobel Prize. But George Penrose didn't get the Nobel Prize for microtubular theory, though, for his work on other more mainstream physics. And Christopher Koch, he had integrated information theory. Again, it's a qualitative, all right? He never had an algorithm because that's probably too much for him. We are the only algorithm for consciousness, right? And we solve many, many million-dollar questions. I will talk about it in a minute, right? So what do you mean by consciousness? So we have a horse here, right? This is in India. We have a natural systems, and we have an artificial system if we have a robot. But these humans are natural. If we have robot, all right. This is in New Delhi, India, and I was visiting New Delhi, and I was surprised that this horse could move ahead without anybody following him. Amazing. I followed him for about half an hour. All right, I was taking the video, and he was getting home. So in other words, maybe culture in India was so good that the horse, nobody will steal the horse, right? Nobody will steal. I don't remember it's a horse or a cow, but he is alone and he knows to get home. So although he did not know that I'm taking video, I'm not sure that he understands video, but he at least has his skill of getting home, right? He knows the path planning, right? He knows how to act, right? He has consciousness, in other words, right? At his level of consciousness. And over here, this guy probably was doing something else. And they passed him right away, very quickly, all right? Now, I will talk about consciousness learning. So here, the animal and non-human animals, non-animal humans are doing learning, all right? And the learning are going on under the guidance of consciousness. Very important, right? Here, I give example of how you train a horse to act in a way so that I can sell this horse. This horse was from a wild horse. Wild horse cannot be sold to an inexperienced people, all right? So he's a professional that trained the horse. He has classes, very much like Xiangwu's classes, you know, how to teach a horse. Xiangwu teach a robot. And this guy has a procedure how to teach a horse, like how to pull him, how later on he start resisting, he start to follow, because I give him reward. I give reward. If he's doing well, I will give him reward. In this case, reward is that touch, all right? Touch this part, right? And then here's the consciousness. He knows the touch on this part is good, all right? Just touch It's good, it's reward. It don't really give food, all right? And the horse is conscious. And gradually do very sophisticated thing, all right? Very sophisticated. If you are interested, go to this website, and he has a professional video to teach you how to train a horse. And very consistent to psychology. John Locke, very well-known scientist. He has contribution in psychology and logic. He said that consciousness is the procession of what passes in a human's own mind, right? He did not have a model, but he has the intuition, and the perception has to do with reception and has to do with our mind, right? And what's the definition of a consciousness? In Merriam-Webster dictionary, you have 5 levels. State of the being aware, state of sensation, emotion, volition, and thought, totality of conscious state of an individual, normal state of consciousness life, and up state of mental life of which the person is aware. I respect the dictionary. This is one of the best English dictionary, all right? Even at the low level, he has something within its oneself, external object, this internal, external. But I tell you the problem. Dictionary is from a person that, or from a group of team members that are not computational. So their definition is very piecemeal, right? I don't want to say it's wrong. It's partial, piecemeal, fractal, right? My understanding of consciousness is not all the 5 levels, right? And not just these 5 levels. Consciousness is, I call, a larger and a higher context beyond task definition, all right? Because our brain for animal and non-animal human never have a task limitation. We just get idea of what they need to do, all right? So it's a higher and a larger context. And what do you mean higher? So this is from low to high, for example, right? But this is not the highest you can get, all right? Not just a person. We also have a value to the group, right? To the nation. Purpose of life. Why we human existed. So that definition was wrong, all right? Not high enough, for example. And larger means have a larger and a temporal context, a longer temporal context, and a larger in terms scale. And because each time we only pay attention to a particular time in scale, and then I will call a longer and higher context in terms of computation. And we'll get to that later on, all right? So I have a new definition in the definition of the consciousness that's more computational and it's more correct. I think it's more correct, but that's harder to understand without telling what. This is the what, right? And what I said, longer and a higher context is not what, but in terms of computation. And so it's harder, all right? It's a conceptual operational definition, right? So consciousness is for social law, nobody. It's not piecemeal, right? And I have a dialogue in AMD newsletter. There is a dialogue on consciousness hosted by Janet. Janet said that we have like 7 responses in the dialogue, and I was the only guy that consciousness must be integrated, right? It's not piecemeal, and all other guys are piecemeal, right? She said that Weng takes a difficult position from the other comments, or different from all other comments, starting from the assertion that all aspects of awareness are tightly interrelated and each cannot function without the others. All right, I'm a loner. I'm the loner in that dialogue, but I already had a model at that time and not published at that time, a little bit early, because I was afraid that if I publish or talk about the consciousness, the paper will be rejected, right? Because we have too many papers was rejected, and including bad papers, and also papers too good. we reject 2 good papers, right? And Christopher talk, he had a scientific American article. Consciousness is everything you experience. It is a tune stack in your head, the sweetness of a chocolate mousse, the throbbing pain of a toothache, the fierce love for your child, and the bitter knowledge that eventually all feelings will end. So I respect Christopher Koch, but this is still a piecemeal account. AI is in a crisis. AI is hot, mainly from media hype. But AI is largely in a wrong track because of misconducts. Right? AI is not nascent. Fifi Lee said, she said in a Congress, US Congress hearing, said that AI is nascent. No, AI is 70 years old. It's too old for human. So it's not nascent. If we have misconduct, we don't have excuse, right? AI is blind. What do you mean AI is blind? Because AI guys, they cover their eyes by hands, but they do not want to see crisis. They don't want to hear. Hubert Redford is not blind. The reason he can make noise is that he is a philosopher. He can talk about things that he does not have burden to do. He said that he has 2 books. The first book is What Computers Cannot Do. Later on, he has another book, What Computers Still Cannot Do. Right? He's a very well-known philosopher. I think in Berkeley, he's retired. He's type 4 AI, non-formal intelligence. He should understand that his non-formal intelligence can be formulated using DN, but he is not ready to understand DN, sorry, right? His activity depends on non-explicit meaning and saturation. That's what the DN can do, right? Learned by perspicuous examples. It's like explicit, not explicit examples, right? Implicit examples. And this kind of program, there's none when he wrote the book. But if he can have a chance to read this tutorial, listen to this tutorial, it's my pleasure to tell Jefford, Mr. Jefford, Dr. Jefford, our DN is this kind of program. And traditional AI is handcraft sensing from word to word, and you have internal representation, and to be conscious about feature. They are not talking about the complete picture of the neural networks or consciousness. They are piecemeal sensation, not integrated, and brittle, right? Because you have 3D model, you have class labels, they are symbolic, and they have a task-specific representations. And in order to address consciousness problem, it's not light, right? I was giving a talk at IJC in 2022, and I was fortunate. This paper was accepted as a poster, and the reviewers are not confident about my paper, and I thank them for accept this paper as a poster. So please don't treat all poster papers are not good papers, right? Like the paper Gestalt, they classify oral presentation and the poster presentation in the CVPI. So CVPR, they found that the shape of the paper, like how many mass you have, or absent of mass, whether you have a color figure, whether you fill the 8 pages, right? We have too many references, or you have too few references, and that's consciousness. Sorry, I respect reviewers, but that's consciousness. That's human consciousness. Because the time is tight, they have to make a decision, right? They close their door to make a decision based on the shape of the superficial paper shape, all right? This paper, of course, can reject it. And I'm fortunate this paper was not rejected. It was as a poster, but I make a YouTube recording, and if you have a chance, you please read, watch this video, all right? Because I think that communication is more important than formal presentation. I just go through these 20 well-known million-dollar questions. The reason I call the million-dollar questions that each problem needs about $1 million investment or more. Most likely not enough, because we have so much money investing in AI, and none of the problem was resolved, right? Another way to look at it is none or all. That's why each problem is so difficult, because if we are short-sighted, we'll not be able to solve any single problem, all right? It's a none or all, right? The first image annotation problem. Retina is without bounding box to learning, unlike ImageNet, right? Our learning is like that, all right? Without annotation, your mother does not annotate your retina. The sensory motor recurrence problem. So all the big data are wrong. So ImageNet is wrong. They give static data, all right? And we must not use big data at all. We must free our robot out, like free our kids to the street, to the rooms, to the human environment, so that they can learn on the fly, all right? Because each sensory input depends on the current motor output. If I turn left, you will see left image. If I turn right, you see right image. You cannot collect the data. All the data assume the action is already there, assume the image has nothing to do with action. That was wrong. It's like you want to train a dumb machine using your dumb static data, right? I will have more going faster, but those are the easier to understand, and later on it's harder, all right? Motor supervision, we don't have motor supervision. We cannot motor supervise anything, right? Sensory calibration, our eye does not need the calibration. Inverse kinematics, your arm do not need to use inverse kinematic compute because our arms is redundant, right? Government free, our brain does not have a government. You cannot just do a convolution, remember, all right? Convolution is a government idea, all right? Closed skull problem. The skull cannot be open and to be looked at by the teacher, all right? Everything inside must be totally autonomous and automatic through entire life. The control brain is a controller problem. Those guys that we have many listeners here are from control community. The linear controller problem has been solved. Brain is a linear controller, but task non-specific, right? So control community is got stuck, right? And the brain is not just a controller, right? Brain is a conscious machine. Causal dimensionality problem, right? The undersample problem. Distribution versus local representation problem. And we have well-known scholars like Azim Loy, all right? Azim Loy said that we have a local representation, yes, but we also have distributed representation, all right? So which representation will emerge depends on the environment of each neuron and the competition. Symbol problem, there's no symbol in the brain, all right? Not like ASCII type, all right? Stop sign is object. Local minima problems. Our brain does not have local minima problem. Our brain is if our model is correct, our brain is free of local minima and it's more or less optimal, right? And our brain can do abstraction on the fly. And a compositionality problem is a term in philosophy means monotony beyond those composed from sentences. In other words, the meaning is outside the sentences, right? The smooth representation problems. Our brain is smooth globally and locally has details, right? Motivation problem, including reinforcers and various emotions. I will talk about later. Global optimality problem. Our brain is optimal, all right, based on a simplified model. Our biological model never be able to say that it's correct because every model of the natural world is approximation, all right? Give example, the Newtonian physics approximation and Albert Einstein's relativity is still approximation, right? Our brain is the first approximation and the first approximation algorithm for consciousness, right? And auto-programming for general purposes and the brain thinking problem. So 70 years ago, Alan Turing asked, can machines think? And I'm here to humbly answer, yes. And we have an algorithm for that. So this is the third hourly break, and it's a good time. Let's have a break. Sorry, maybe 5 minutes. If you have question, please. Let's resume our last hour. We have last hour, resume our talk. This is a picture that explains why the model here was so difficult to understand and so difficult to come up with. So the brain is like the elephant, and each discipline is like a blind man. Blind man, biology, neuroscience, psychology, electrical engineering, computer science, mathematics, maybe including physics, but somebody said that physics everything, but physics networks are very limited. So in this sense, with due respect, all these scientists in related disciplines, they try to go about multidisciplinary research, but the scope is limited and the depth is limited, and still very much a picture of an elephant and a blind man, right? And you probably ask why I can see a picture of that. Just a short answer. This is a long answer that will be in my book. A short answer is that I was fortunate, right? First motivated because I was raised in a very harsh environment in China, right? Most obvious thing is the poverty, right? Highly motivated. And also the training in the Chinese schools are very solid. Some people probably disregard it as exam oriented, but extremely important, all right? And give example, the math class that I learned at the Fudan University was very, very solid. Although not everybody in my class enjoys that, right? So the training that I got in Fudan University, especially in math, was not available in the United States for undergrad. All right, that was undergrad. Those courses, the material was a math major in grad class in the United States. But after I got to the United States, I get chance of being advised by a professor in electrical engineering. My degree is in computer science, and I'm very interested in mathematics with solid training in Fudan University. And my two advisors are both in electrical engineering. I was shocked that for the system signal processing perspective of electrical engineering, and some of my perspective are from their electrical engineering background. And I had after I got a PhD, I have a chance, I'm motivated. Basically, I sit in class of psychology and neuroscience and biology. And Brain Mind Institute has classes that I organize with others, and we hire an expert to teach those courses. And I had the experience of doing sabbatical research at the MIT in the Department of Brain and Cognitive Science, and I was learning biology over there too. So in that sense, I do not have degree in 6 disciplines, and I have only 1 degree in computer science, but I have enough experience for me to come up with what I have right now. Although they are still not enough, I hope that my life can live much longer so that I can learn more. But you know, our life has a up limit, right? I'm not sure I can go over 100 years, but right now, that's why I feel that the time was so tight for realizing conscious machines. So human does APFGP, auto programming for general purposes, right? For baby example, they build a toy house, right? And what's the minimum mechanism for baby to build a mechanism, toy house, right? That's any house, for example, that can come up with, right? And for adult, they build a car, right? So what's the minimum set for adult to build a car? Why robot need to do APFGP, right? So the AI revolution, robot must learn on their own. We cannot spoon feeding robots, right? And robot must learn consciousness, not just sensory motor behaviors, but also consciousness through lifetime. And the picture of solution major problem in AI must have a holistic solution. And what do you mean by conscious learning? The consciousness not handcrafted because too rich, too large in scale, too long in time, too high in abstraction levels. But we find a minimal set of mechanisms. And we have emerging model that's holistic, right, detailed in computation, so they can implement it, you can verify, proof or disprove in independent libraries, labs, and it's an overarching mechanism, and can develop small and large brains. And lifelong learning that's conscious for a higher consciousness, right? And at the younger time, you have a lower consciousness. At a higher time, later age, you have a consciousness. And for example, at that stage, you probably want to get a good grade, but later on, you find out that get grade is not enough. I want to do better for my life. And at that age, you want to say, I leave something behind, right? So the consciousness is not just outcome of training, but also causality in the sense that your consciousness guides your correct learning. Without consciousness, you will not be able to do the right thing or think the right task in order to learn what you need. So by definition, consciousness is consciousness by a biological or artificial machine, is that a learner is conscious throughout its lifetime learning. It bootstraps its consciousness from defaultly conscious to increasingly conscious to maturely conscious. There are 3 categories of tasks that was proposed in the first edition of my book, and also richer in the second edition. The first task category is clean. The second is muddy, and category 3 is very muddy, right? And the tutorial of material is very much covered in the book, and I encourage you to get a copy if you like to read more about it. And the GNSMR we mentioned several times that correspond to 8 properties: G for grounded in the physical world, E for emergent representation, only emergent representation, no symbols. N for natural representation for sensory effectors, I for incremental computation, not batch learning, S for skull closed, A for attentive, N for motivated. Emotion is a special case of motivations, like hate, and I'll talk about later on, jealousy, right? And drive, volition. A for abstract, not just fitting data. Also, must also abstract rules autonomously and not taught. GNSMR are all necessary, right? Our solution is that grounded is using real robot. Emergent and the human is not in the loop of symbolic school, give label, class labels, right? And the incremental learning, right? And those network, well-known networks, they all break those rules: skull closed, attentive, motivated, and abstract. And I'd like to mention 2 papers, right? And that's in the ICDO 2020. And this is the early this year in the HP Transact 40th International Conference on Consumer Electronics. It talks about 3D to 2D to 3D conscious learning. And in order to learn any consciousness, so you cannot have a fixed number of areas. So the architecture must be fully fluid. So the solution is from our DN2, right? You have negative neurons. So positive neurons need to find their competitors. So negative neuron is associated with positive neurons. So you have positive neuron pairs, P for positive and N for negative. So in biology, negative has certain density, and positive neuron have certain density, and they have certain densities, and statistically, and then you have each positive neuron ever have one or few negative neurons. But for efficiency, we assign each positive neuron to a negative neurons. And a positive neuron fires if and only it's an N, negative neuron does not fire. That's a simplification. As I said, that our model is a simplified model for the density-based positive neurons, like pyramidal neurons, and negative neurons, like GABAergic neurons, right? Then the negative neuron uses LCA to find all the competitors, because if the P neuron fires and N neurons will not fire, but if P does not fire and the competitor will fire, right? Then the N will link all those competitors up to a certain degree, all right? If it's too far away, not nearby enough, and it will not. So only we'll find nearby competitors, because the cost of competition is high, and the cost of connection is also high. And US patent number, well, we find this one still pending, all right? And the first journal paper about DN2 is Wu and Weng in IEEE Transaction on Industrial Electronics 2019. Another important concept, which probably many people said, oh, it's not necessary, is the brain patterning must from a single neuron. Right? So the DN2 you spawn, but does not start from single neuron. DNC will start from single neuron. So you have a single neuron for the brain, then it will becomes 2, becomes 3, 4, and so on. And over time past, you have a birth. Then you have infancy, you have adulthood. Then it becomes richer. This allows you to spawn neurons one at a time from parents' neurons. And child neurons are like parents. They are similar to parents. They copy the weights from parents, copy the connections, but they start with a 0 age, so that they become very plastic. And the brain's global smoothness is maintained because you don't really need to decide how many neurons you need for each neuron, each area. And the global smoothness is maintained, but the local details are also maintained because you have a local learning, right? Then cost to find is a practical solution to automatic brain patterning, right? Brain patterning, how brain form over 40 areas, and also more detailed structure of areas. That's proposed by the cost to find scheme of DN2 and realized in DN3 from single neuron. And the paper was a patented patent application submitted, and the biological model was rejected by Nature Science and PNAS, neural networks, and all this direction. They did not even go to peer review, and ARXIV even. And I don't know why ARXIV reject the paper. ARXIV is supposed to not do a peer review. Is that a pseudoscience? I don't know whether ARXIV archive feel to add the pseudoscience paper, but there seems to me they are doing peer review, right? The research square, after rejection first, research sphere can give me another email. Maybe they got some information from Nature. I don't know. I don't have evidence. They tolerate to post my paper, but they said that this is not citable by media. But at least it's publicly available now. And you can see that people that are acknowledged in the research square report have read early version of the work. That's the first conscious learning algorithm proposed. So when we do teaching, you supervised mode, we mean that we supervise the mode, right? But for human, you really cannot supervise everything, right? For example, for this case, mouse is not supervised, legs are not, all right, and the hands are only on the hands. And unsupervised means that we need to release our robot free so that it can learn autonomously, real time. Now talk about motivation. We mentioned a few times earlier, and we classify all the neural modulators into 6 classes. We have potassium-based, then we have inhibitor-based. Potassium-based is the excitatory, and inhibitor-based like GABA, right? And that's a positive neuron, a negative neuron. Then other 4 classes is serotonin 5-HT, and dopamine DA, acetylcholine SH, norepinephrine NE. And serotonin is a class that for pain, stress, and punishment that animal try to avoid. Brain synthesize serotonin when it get something bad, actually, like pain sensors. And the dopamine is something that human want, like pleasure, wanting, anticipation, rewards, including like sex. And acetylcholine is for expected uncertainty, and norepinephrine is for novelty or unexpected uncertainty. And that's according to a published paper. But that's only approximation. And we use these two neurotransmitters, modulators. Basically, if you use for emotion, then it's for modulator. And we use that one for the synaptic maintenance. And acetylcholine represent standard deviation from match to the weights. Norepinephrine from the deviation from standard deviation, all right, and normalized by each neuron. So each neuron has its own novelty. In terms of transmission, for what we learned so far, most is point-to-point. So a neuron fires, then they have axons that leads to the synapse of another neuron. That's a point-to-point. Growths are slow, but very precise. And another is called release hormone into the blood that has to do with growth of the body. So basically, human body will synthesize a growth hormone and release into bloodstream, and bloodstream will seek out through the tissue, then gets into the cell. That's a slow, but it's extremely important for development. That's how we have a height at different age. And autonomous nervous system, those are the nervous systems that controlled by your vital activities like heartbeat. And those networks are still learned, but mainly based on body experience. And a single neuron will be amplifying to many neurons so that our brain will control the heartbeat, for example. Before your birth, your heart is already learned to beat. That's from, it's a wiring experience. Each neuron still learn, but based on the wiring experience and the signal experience, like human retina has spontaneous activity that was very critical for the wiring of the retina and LGN, right? So experience play a central role in the building autonomic nervous system. And that's what we will talk about more. It's called diffused modulatory system. That's a neuron will synthesize neuromodulator like the 4 class we talked about earlier. Then it will release into the tissue near neurons. Then those signal will affect almost every neuron in the brain. And you will see that, all right? It's a diffused in the sense it's not precise like 1-to-1, but rather a certain kind of neurotransmitter modulator will be diffused into many cells in the brain, and they all get the punishment reward like that, right? They can also take advantage of ACH and NE. Brain is a grand UTM, and you may have multiple Turing machines, and each Turing machine may have one or multiple universal Turing machines. There's no clear boundaries because they share feature with one another. And here, give example of you have a network that learn the task, multiple tasks. In this case, task 1 and task 3, where task 1 is the simple represented by a transition table, and this is symbolic, so you can understand the task. In this particular case, very simple task. If you read the paper, and that's a muscle representation, that's a pixel representation, 3 pixels. Then you have another task 3 on top of that can be used to call the lower task 1, and put together you have a grand transition table represented by a single grand Turing machine. And if you get rid of all the symbols here and becomes patterns, this means this neuron does not fire, this neuron fire at one. And so those are spiking neural networks. From this one, it's very difficult to get the picture of original task representation. So that's why I think that connecting project is not very useful, because you get signal, you get connected patterns. Those are more detailed, but detail is not really critical for understanding, right? It's the rough connection that helps us to understand. And also actually plasticity helps us, right? But not the detailed static connections. I'd like to discuss Church Turing thesis, which state of its function on a natural number can be calculated by a paper and pencil method if and only if it's computable by a Turing machine. That's a hypothesis, and there are different ways of saying it, and this is a more easier to understand version. And this thesis cannot be proven by a formal method, according Wikipedia. But I proved it using theorem formalism and also extended the proof. It states that, right? For any machine, natural or artificial, the following ABCD or ABC are equivalent in terms of computing engine. They basically use the same engine in FA, emergent. A, its Genesema augmentation learns and auto-programs for general purposes in real world. So it's emergent in the real world. B, it computes all functions that are computable using a pencil and a paper method. C, it computes all functions computable by any Turing machines. A and B are assume that the machine has successfully learned, right? Because everything needs to be learned. C assumes that the Turing machine has been correctly programmed, right? Because this is learning a Turing machine that's correctly programmed by a human. So with that, we are able to prove it. The idea of proof is like this. I just give you an idea, all right? For detail, you should read the paper. The A is grand Genesema UTM. B is any paper and pencil method. C is a Turing machine computable. And we prove by start with the A, right? That's our model. Then we specialize that to become B. Then we specialize to become C. And a C go back to A is very difficult. C back to A is difficult. That's our method, right? And we prove mathematically. So then they are all ABC are equivalent. We do need a robot. So we have a robot. There's a cell with Dell. We constructed at my lab at MSU. And that's a processor that I outfit from Highlander Toyota. And that's from Flying Fox, AVS company. They build laser scanner. And that's their vehicle outfitted in AVS. And I appreciate their collaboration with us in the first startup competition. And we have very impressive robots, Boston Dynamics. You probably can get video, but they are task specific, make a real demo, real-time demo, but learning is not real-time. And over here, a tool provided an inexpensive outfitting of automobile with most of the controls, including the steering wheel. Now it's running autonomously. So this is my Toyota that has a comma 2. Here's the interface, comma interface that costs you only $20. Very impressive. It used to be you outfit a car will require you about $50,000. Now it's only $200 if you provide, you have a car, a more recent model, they already have a forward-looking camera and has all the motor, they're called drive-by-wire. Then the controller using camera is called comma 2. Now they have comma 3. I think function are basically the same, but hardware is better. Using lane tracking, comma 2 are 1,000 and comma 3 is 2,000. And there are many newer models can be compatible with comma 2. So look at their website. So in other words, that outfitting a commercial car is easy. It's available thanks to the work of comma. So the learning need to be conscious. If we have a robot like a robot car I showed earlier, and a conscious learning, and the consciousness is not just outcome, but also causality, as I said earlier. And learning is 3D to 2D to 3D. So the real world is 3D, like your hand, like whiteboard or blackboard. And you get your image is 2D, and the image need to generate action. Action is 3D and end to end. 3D space of the real world. 2D is sensory image and motor images because our motor can be represented in the 2D map in the muscle array. And you back to 3D world in the real world. So learning must be real time and incremental and trial and error without using inverse kinematics, because our hand is controlled by a redundant arm, and arm is controlled by a neural network, and learning must be trial and error, and you learn inverse kinematics on the fly. And so that's the recall that hopefully Boston Dynamics in the future can use our brain chips to teach their impressive robot to learn on the fly, like human learn doing tumbling, somersault. All right, so conscious learning, there are several conditions. All right, first you need 8 conditions, Jenny-sama, and the life required degree of real time, basically at the scale of milliseconds. If you are talking about our normal human response speed, like on the order of a millisecond, like driving, you need about reflection rate about 100 Hertz. And for emerging universal Turing machine, and you need to have a capability of universal Turing machine. Otherwise, you cannot do a conscious learning. And here is SEB learning mode. S for skull internal representation, E for effector, B for bias sensors. So we have a binary representation. S could be 1 or 0. 1 means supervised internal representation. 0 means internal representation not supervised. All right. And E1 means motor supervised, motor imposed. 0 means motor autonomous. B for 1 means bias sensor is used. 0 means not used. Right? And a binary code ESEB at any time from the environment. So this signal, environment decide which you have, all right? So SEB will have 2 times 2 times 2, you have 6. So you end up with totally 8 types. Right? So it's not just supervised learning or unsupervised learning. So now, so we will recall unfolding in time. Now over here, we have a context here. This is C0, three components, you get C1, C2. So the context learning in real time, the transition in real time at discrete time. And APFGP in DM is also in the real time. That's our recall. And we need to understand how imitation can allow simple to complex conscious learning. So you need a conscious learning agent with the features that we had earlier. And in the action sequence imitates a 3D event that typically from a real world or from a teacher. And a human needs to judge whether it's similar or not, depends on the age, all right? Depends the sophistication of the task, depends on also the judge, right? And learning must be autonomous, and the factors are not teacher imposed. If imposed, it's not simulation, not imitation. So here example of how a baby, right, can imitate. So teacher places a foam on the ear, one ear, and the child places a hand foam on another ear. I say an ear because here is the left hand, here is the right hand and right ear, and here's left hand and left ear. So there is a discrepancy, all right? And creativity for teacher is self, right? Teacher is doing self. And the hands are different. So self becomes from teacher to child, that's creativity, right? And the child cannot do this exactly the same as a teacher because she is younger, right? She is a child and should not do something that on the mother, but she was doing invention in this sense that she changed the subject from teacher to herself. And she also invented from left hand to right hand. So in this example, that creativity already takes place, all right? In other words, creativity is from errors, right? Or impossibility of repeat everything. Why imitation? Theory 1. And imitation reduces teaching complexity. So you have n stages, n variations for each stage. And you have S as receptive field size, and you have totally B neurons. And the brute force data fitting, you require all the combinations, right? M to the N training examples, and you consider the receptive field, you consider number of brain neurons. That's an extremely large number of training samples. But super imposed, and you reduced it, all right? You reduced it because that's a supervision number of variations and number of stages. You have M times NSB, so totally reduced, right? You don't need to try an error. Everything is supervised, taught by the teacher. But imitation first reduce, all right? Imitation, the practice of M, what you do is at home, all right? And the classroom only give you N demonstrations, one for each stage, all right? And N practice at home, and the computation is going on at home. So the total complexity tremendously reduced from exponential to products to ON. That's how teaching is just an example in class. So I need to design N classes, right? For example, this one I teach one class and I teach two classes. The second class is based on the first scale, and so on. In N class, I based on previous classes. Then all the dash line was practiced like a homework by the learner. And a single motor imitation, our goal is to have the same equation, same mechanism from simple to complex. All right, so we have the same network. So early imitation, early practice action, the innate is emergent from volume, right? Body learned is automatically invoked later on from associated event, X event. So basically, from the innate action, you will come up with the sensory input. That's on physics word, all right? Then when you are doing that, your sensory will lead to your Z through your brain. This is from external word that's loop inside your brain. Then because this one will lead to Z, originally triggered by the innate behavior. Now the Z effect will trigger your behavior. That's single motor imitation. Innate, sensory input, action. Then once you see similar sensory input, you generate the imitated behavior. This behavior, ZXZ, will repeat for complex words. Still ZXZ, and not multi-imposable. So multimodal imitation and multimodal capability is a later time extension from the early imitation theorem by extending the Z innate to an early practice sensory motor action Z motive. And that's practiced. Like giving up, this is going to class and requiring more fine-tuned motor YM in the network that tune their receptive field to more relevant sensory object X, right? So this is like I'm doing my homework. This is seeing my class examples, right? That are also sensed from sensory motor concept event. So this one is what I go to class, then I see my teachers doing that. Then at home, I can do the same from what I see, similar to what I see in class from my teacher. Then I can generate my practice example from what I did at home. And what I see my paper, I see my pencil, I see my book, and I can generate my action to the imitation. So this is in classroom. This is at my home. If the autonomous imitation is for a long sequence of events, the above arrow indicates triggering the starting context of a corresponding event emerging Turing machine that display the event. So if this is long, and this could be very long too, right? So this could be like learning Chinese at home. This is like writing Chinese novel. We don't need a motor imposition. So the creativity, all right, is general through imitation. Theorem 4. Thoughts by a natural artificial agent via autonomous imitation of a 3D real-world events are of general purposes per universal Turing machines. If the imitation result is judged considerably different but creative, such autonomous imitations correspond to creativity of the agent in the judge's eye. So this happening in real time, and sometimes could be like a child play, and mom look at it, maybe, oh, this child is a creative. And if it's a child play, becomes the teacher's play, and the teachers become doing scientific research. And we have Brainmind Institute to teach all the background that I touched upon during these talks. And we have 811, 8121, and we have also competition in context. And the class, we learn stuff from 13, and the later class from 14 and 12. And each class has a video, PPT file, and exam grading. And if you pass, you can have a course certificate. And context is the only context that's task then specific. So you don't know the task, right? And we have limitation on the number of neurons, and you can use, and it's modality independent because we have different modalities, and each full-time student pay $150 application fee. You can have 3 courses, and you can attend a workshop, and you can have a context entry to participate in the context. And currently we have a issue of what I call brainwashed. We have papers are already on APFGP learning theory, and from 3D world to 2D. And for 3D world, we teach 3D world, but this was accepted by CDL, but this paper that teach from 3D world was rejected by the next year's ICDL. And this year, we have a biological model that was rejected by as a conference. So our reviewers are very, I don't know how to say it. It's repeating the history. So here I'd like to give some brief conclusions. We have a complete theory, right, for general purpose imitation based on Turing machine, emergent. Learning 3D events directly, then we create behaviors in the 2D model. Then the machine carry out programs in 3D. And a major advice here, take-home message, is that without motor imposition, it's free of any annotation. So learning is totally autonomous. The conscious learning proposed here is probably a paradigm shift in AI. How soon? We don't know. It depends how the research community is open-minded. And human-like conscious learning on the natural intelligence side is theoretically sound, modeled, but the correctness or more detail need to be verified by many independent labs. So we do have a challenge in the future. The one immediate challenge is brain size humanoid chips learning at about 100 Hertz. That's very challenging. Our group have a team of creative researchers. They are working with me, all right? They build hardware and the chips for future brain size robot to learn in real time on the fly to demonstrate consciousness, and possibly also hopefully to verify the correctness of developmental networks for biological brains. All right, thank you very much. That's the end of the class. I'm sorry that the time is late. I used a little bit over 4 hours, and the tape time is not 4 hours, but the real time is a little bit over 4 hours. It's 4 hours and 8 minutes in real time. And I'm not sure that we still have people around. We still have a few people dying hard. Thank you so much for staying around. You can share your camera if you want. Your images will not be recorded. We are currently still, wait a minute. It's up to you, all right? Currently, your answer, your question still being recorded. If you don't want to record, let me know. But please tell me whether you have any questions, clarification, comments, whatever. we already have some question earlier, all right? It was answered during the break time. We had 3 break time and 3 hourly break during the presentation. During that time, I did not record, but I wonder whether we still have some people who like to ask questions. By the way, I plan to post the video here to the YouTube with the same title. You probably can find out called BM Talk, BM for brain mind, BM Talk, a single word, and you should be able to review the video. If you don't have time to complete, you can pick up from the YouTube Talk, right? You can also ask questions there, and I will visit. Sometimes people will make comments. I already had some comments in the BM Talk video there, and if you have a question, you can ask there too. But let me know. Do you have any questions? We still have quite a few people still watching. I don't know whether you have any questions. I'm sorry it's late, right? Probably very late. Some of you, many of you already after the midnight. That it's in the United States, it's a noon time, and 1:23, and UK is the evening time, and in Asia it's very late. My apology. Any questions? All right. Any question? If you can raise your hand or just speak. All right. If you don't, and then I assume that's the end of the tutorial. Thank you very much for your attention, and thank you very much for your questions. I pause recording right now. Bye-bye.